Hi everyone, I think we're going to get started. So to those in the back,
Yeah.
I'm looking at you.
Guys, cut it out.
Okay, so welcome back everyone to the RL Bootcamp Day 2. Today on the program we have, the morning is our keynote lectures. The afternoon we have 2 more lectures and then the kind of bulk of the hands-on tutorial. So we're going to start this morning with Kai Dresia. He is, oh no, I lost my notes. He's working at DLR on the Institute for Space Propulsion. He has his master's in aeronautical engineering and just finished, I think, his PhD, just handed in his PhD. And the topic of his PhD is using deep reinforcement learning for rocket engine control, probably the coolest topic or use for RL that I know. Since handing in his PhD, he's now group leader of System Analysis and Control Group, and today he will talk to us about reinforcement learning for rocket engine control. Looking forward to your talk.
Yep, thanks. So in fact, handing in the PhD thesis was the best day of my life, so now I'm really happy. In fact, it's not my first day or first time in Austria for reinforcement learning. Like 2 years ago, I was invited to Vienna and had the pleasure to give more or less a similar presentation. But now we have 2 years later, we have way more results and way more cool videos I can show you today. And for me, it's really great to be here to talk with people who are also experts on reinforcement learning. In the space industry, people don't know machine learning, and you always have to start from the beginning and talk on a very low level. And it's great to have here people who also know this topic. So yeah, I'm from the German Aerospace Center, and we are one of the largest research institutes in Germany. We have plenty of sites in Germany, and we are also testing rocket engines. So we are doing a lot on like climate research, on transportation, and so on, but we are also testing rocket engines. And this we are doing here in Lampolzhausen. It's a very small village in southern Germany, north of Stuttgart. And yeah, we have the largest test facilities for rocket engines in Europe. And here you can see a video of one of the latest large tests. And you can see it's quite large. I will show you more details on rocket engines, but just an impression how large the test facilities and the tests are. This is our site. So we have multiple test benches here, P2, P3, P4, P5, where we test different scales of rocket engines for different applications. You can see some pictures of this. So just for scaling, the right one is the largest one. It's, I think, 3 meters in height. So it's quite large. And you need a lot of space, and this is why we are in the middle of the forest in this place, because like 40, 50 years ago, they searched a place in Germany far away from civilization, and this is the place. Okay, but what are rocket engines? So you might have seen some pictures of launch vehicles. This is the Ariane 5, Europe's largest transportation vehicle for space transportation. Okay, no pointer. Oops. Okay, whatever. This is the rocket engine, and the rest of the rocket is more or less a tank for fuel. So 90% of this whole structure is filled with fuel, and only the top 5% are the payload, so the satellite or the mission payload that you send, for example, to Mars. And here you can see the rocket engines. Typically, you have 2 of them, one for ground firing. So when the vehicle is started, you use this larger engine, and then after some time, you throw away these outer boosters and the whole lower structure, and then you use the upper stage, which is optimized for vacuum, for space. And there are different types of rocket engines. We are using rocket engines which use liquid propellants. So one problem is in space you don't have air, so you don't have oxygen from air, so you need to bring your own oxygen. So you have a large oxidizer tank, it's typical just liquid oxygen, and then you have a second tank, the fuel tank. Oops. And you typically use liquid hydrogen or methane as propellant. You need to burn those propellants here in the combustion chamber, and then you expel the hot gases through a nozzle, and then you just use like conservation of momentum to propel your vehicle forward. So now the question is, how do you get the propellants from the tanks into the combustion chamber? For this you use pumps. So you have typically two pumps, the oxidizer and the fuel pump there. And now the question is, how do you drive the pumps? So there are options to use electric pumps with batteries, but you need too much power for the larger rocket engines. So you typically have a turbine, and then the question is, how do you drive the turbines? And for this, you use a second combustion chamber, the gas generator here, and you also burn a small portion of propellant there, produce hot gas, and with this hot gas, you drive the turbines. The turbines drive the pumps, and then the pumps pump the propellants into the combustion chamber. This is more or less the basic principle of rocket engines. And now, for us, for control, you need a way of controlling these engines, and for this you have typically 2 to 4 valves, just regular flow control valves, which can regulate the amount of propellant to the combustion chamber, to the gas generator, to the turbines. And yeah, then you have this large scheme of rocket engine control. So the basic goal is you want to control the thrust of the rocket engine. It's the amount of force, and you need to precisely control the amount of thrust. You also need to control the ratio of oxidizer to fuel. Too much oxidizer results in high temperatures, might damage your engine, so you need to precisely control this. You also are always operating at the limit of all materials, so in temperature-wise, for example, so you need a way of controlling certain parameters so that the rocket engine does not burn or melt or explode. So you have those 3 control tasks, which you can do in closed-loop control. You also need a way of starting and shutting down the engine, but this is typically done in open loop, so you have pre-programmed sequences for the valves, which are tested on the test bench. Yep, in terms of how and what you are controlling, so you have those flow control valves, which you can control and use, and they are based on simple sensor readings like pressure or mass flow, which you have placed in different places of the rocket engine, and yeah, those sensors can be used to read the state of the system, and then hopefully find a nice control strategy, in our case then reinforcement learning, that can control the thrust mixture ratio and more constraints that you do not want to cross. And why do you need it? One example is when you want to land your rocket engine back on Earth, which Elon Musk is doing for some years now, you need to control your thrust very precisely. Otherwise, you will crash, and that's bad, of course. And it gets more complicated, for example, when you have not just one engine, but for example, Elon Musk with his Starship, now he's using more than 30 engines at the same time. So you need to control all of those 30 engines at the same time. A quite complex task then.
But as Marius just pointed out, it's lunar lander, basically.
Yes. In fact, we started, I think, 5 or 6 years ago with lunar lander. Yeah. Okay, but why is controlling rocket engines complicated? So one basic principle is that it's a MIMO system. So you have, for just the very simplest version of a rocket engine where you have just pressure in tanks and you're using two valves for controlling the oxidizer and fuel, and you want to control the total amount of propellant, which determines the thrust of the engine, but also the ratio of oxidizer to fuel. So both lines are coupled, and you need to control both similar and in a multi-output, multi-input, multi-output fashion. So this is a problem for most control algorithms. So there are ways from classical control which you can use for MIMO systems, but it fast gets complicated. So one example of rocket engine control was used for the space shuttle main engine. You might know the space shuttle, so it's like the best researched engine ever. Today we're also always using data from the space shuttle because NASA published everything, and this is great and not very common in rocket science. So yeah, their approach was to use two decoupled PI controllers. And this is possible, but they had problems because the decoupling introduced some problems. They damaged the engine during some phases, and it's working, but not the ideal optimal solution. So different approaches, for example, model predictive control, MPC, or reinforcement learning are options for the future, which can help to control the engine in a more optimal way. Okay, so we are machine learning guys, so our approach was to use reinforcement learning, and some arguments for this are the hardware, the computing hardware on space vehicles is typically super slow because they need to deal with vibrations, large temperatures, radiation in space, so you have limited computing power. And reinforcement learning, once trained, it's just a small neural network, and it can result in very high control frequencies. We can also use directly simulation models, which we typically have for designing the engine. So we can use the knowledge of the system analysis guys and directly use those models to train the controller. And in the future, if we have reusable rocket engines, so we land back on Earth and then start again, there are some problems. For example, the properties, the efficiencies of components might change over time. Or we want to reduce the damage to the engine or operate the engine at maximum efficiency. All those factors can easily be implemented in the reward function, and this is a unique property of reinforcement learning, and it's not so easily done in other control approaches. But of course, we know robustness and safety and stability concerns are a problem, so we need to convince people who are launching 500 million vehicles into space that they should trust reinforcement learning. And I guess that's quite a challenge. Okay, so 5 years ago, we started the research and asked us some questions. So can we demonstrate reinforcement learning control experimentally on a representative rocket engine? So our goal always was to take existing algorithms and ideas and use them for our application and test them experimentally. Because in simulation, we know we can do and solve most problems, but going to the real world is, in most cases, the real challenge. And that's the second question: can we only train in simulation and then directly go to the test bench? Because testing is super expensive. So for example, the largest tests cost 200,000 euro per day, and even the smaller ones with 20,000 euros per day, it's too expensive to train the controller on the real rocket. And then the question is, how can we deal with stability and robustness concerns? Can we maybe find hybrid approaches, coupling reinforcement learning with classical control to make the controller more trustworthy? Okay, and for this, we decided on two test cases. So we have a turbo pump. So this is more or less the pump on one side and the turbine on the other side. and the control is quite easy. So you have two valves, you want to control two properties at the same time. They're not really coupled, a little bit, but not that much. So controlling this system is quite easy, but we wanted to try it first on this system because it can't explode, and that was good for my heart. And yeah, the second one is an entire engine which we have developed in Lampertshausen on our own, and the control of this system is more complex than for typical flight-like engines because it's a research platform. We have more control possibilities, so controlling this system was and is quite challenging. So the first one we did 2 years ago, and we tested this at the test bench, and here you can see the two quantities we wanted to control. It's the outlet pressure of the pump and the mass flow. And you can see these are here experimental results. It worked quite well, and we did a small PR stunt and controlled in a way so it's the DLR logo. Oh, nice. Okay, but this was great for us. So the guys who are responsible for the testing activities now trusted us, and they said, okay, you can do it. We know everything will work. But we knew that controlling the entire engine would be quite more a challenge. Okay. And the system we wanted to control here is the Lumen engine. So it's an engine which does look a little bit strange compared to the engines you have seen before. The reason is that we decided to not integrate everything onto the engine itself, but like spread it far away from all components. So you have the combustion chamber in the middle, and then the turbo pump like 3 meters away, connected with large pipes. You have control valves everywhere. So like here's one, there's one. So many control valves. And the reason is it's much simpler to build, and you can change parts and so on. So it does look a little bit strange, but this is a real rocket engine. And from like the components and the architecture is quite similar to real flight engines. And this is our 5th largest test bench, the P8. And yeah, the combustion chamber, it's maybe this large, this diameter. So it's already a large rocket engine. The scale, it's for upper stage applications. So when you remember the scheme of rocket engines, you have the first stage and then the upper stage. So it's an engine for use in vacuum. It uses liquid oxygen and methane. It produces 25 kilonewtons of thrust, so it's quite a lot. So 2.5 tons you can lift like straight up with this engine. And just for scaling, we produce 60 bar of pressure in the combustion chamber. And to do this, we burn like 8 kilograms of propellants per second. So it's quite a lot when you compare it to your regular car, which uses just a few grams per second. And the cool part is we convinced the guys that this engine will be in the future, and is right now, a platform for testing, control, monitoring, sensing applications. We have so many sensors and control possibilities that it's more or less the best possibility to test those algorithms. It took a while. We started testing each component individually, but this year in February, I think, we put everything together, and here you can see the first ignition and the first test of the engine. So we, of course, have a drone, and here you can see the test bench. The engine is here, and this thing is not part of the engine. It's just a guide tube to guide away the flames, because here is a forest and you don't want to burn the forest. So the flames are diverted to the top. So don't be confused, it's not part of the engine itself. Okay, now they told me, okay, next time it's your time, you have to control it, and my heart rate was quite high. But what is the goal? So here you can see a schematic of the engine. So the architecture is that you can control the combustion chamber pressure here, the ratio of oxidizer to fuel, two properties. We are also using the propellant here in the combustion chamber walls to cool down the structure, because otherwise it would melt. And we also want to control the temperature of the methane, which is then here injected into the combustion chamber. So we have four control variables, and we use four valves for control. So four variables for actuators, so it seems to be a reasonable problem. And we want to change the combustion chamber pressure from 40 to 60 bar, keep other properties constant, and change the cooling mass flow depending on the combustion chamber pressure. You can imagine higher pressures need more cooling. We want to have like ramps in the thrust or in the combustion chamber pressure. We use those four valves. Want to have a controller with 20 hertz and get a low steady state error. And we need to be robust against quite large sensor noise of up to 1.5%. And we need to be robust against some modeling errors. So we have a simulation model I will show you later. And we need to be robust against like all kinds of uncertainties in this model. And the goal here of my presentation, I thought, was to be, okay, now you have seen all these requirements. Now the question is, how can we train a controller which can do this in the real world? So in terms of reinforcement learning setup, we decided on the soft actor critic algorithm. Some reasons are that it does not need a lot of hyperparameter tuning, because we wanted to focus on the control problem, on the engine, on the robustness, and not on training 20 controllers with different learning rates. And this algorithm is quite robust. It's suitable for continuous state and action spaces, which we have here, because we can sense everything in a continuous way, and also the valves can be set to every possible position. And one small detail is some research have shown that those kind of algorithms which use entropy in their formulation, so it does not only maximize the return, but also maximize the entropy, are quite robust in real-world applications. So we decided on this algorithm and then generated some training episodes. So you have here different profiles of combustion chamber pressure, and one really important aspect is that during the training you need to have similar trajectories, of course, as you want to test later in the experiment. And yeah, so our approach was to just train on different trajectories and then test it.
What entity do you mean the neural network parameters?
Of the actor policy, so then you get maybe not it's a stochastic policy, and you maximize the entropy of the policy. So more or less, you try to find the most random policy that still maximizes or optimizes the control problem. Okay, and for training, we first start with the nominal model parameters to get the algorithm a chance to learn the physics of the system, and then we step by step increase or change the model parameters, and in the end add also sensor noise, like in a step-by-step approach. So start simple and then increase the difficulty of the environment.
But what's your reward? What's the signal that it's doing everything
It's
correct?
coming on this slide. Yeah. So the next two slides are action space, observation space, and reward. Yeah. So the action space is quite simple. We have our four valves, which we can use in a certain area. We found out some limits with our system analysis. So we reduced the possibility for the agent to control it in like from 0 to 1 to make it a little bit easier for the algorithm. The observation space, it's quite large. So we have this observation space. So we use all 4 values which we want to control. It's the y. Then we also include the reference values which we want the controller to set. Then we have some additional parameters, some pressures in different parts of the system, which helps the controller to find the optimal solution. They are not really necessary from like a physical point of view, but some simulations showed that they help the control. We also include in the observation space the position and commands to the valves. So the controller knows the current position and also which command signal it has sent to the valves in the previous time step.
Excuse me, in the observation space, all those variables, did you have a sensor specific for them?
Yes.
Or did you use observers?
No, we have sensors for everything. That's the nice part of the Lumen engine, that we have many, many sensors. Okay, but then we also extend the observation space even further. So this is the direct sum. So I'm not a math guy, but apparently you can use this direct sum to stack vectors, and it results in a larger vector. So more or less we take the observation from just one single step and the previous few steps and put it all together in one large vector. So more or less the controller sees the current and also the last few time steps of all variables. It's more or less the same like including derivatives or to use recurrent neural networks. So there are some discussions which way is the best. For us, this was the easiest one to implement, so we decided on this. Yeah.
I would have a question on the observation. So what does this mean? What is the size of this vector? Is y just one variable which is derived by the right side variable?
No, so y are 4 variables.
4, and
so
it's really a
it's
combination of these
yes.
variables. Okay.
Yeah, so in each time step you have those 12, 15, I don't know. And then you add up, in our case, I think 3 or 5. So you have like 30, 40, 50 as the...
For the observation stacking, the case, like you have like 10 observation in the past of like 1 millisecond of time step
Yes.
in one observation.
Yeah, yeah. And then you stack everything together, and by having like what pressure was there like 10 milliseconds ago and which pressure is now, you can of course just calculate the rate of change. Yeah.
Is this observation stacking done in order to preserve the Markovian process?
Yes.
You have also
Yeah.
information about the past time?
Yeah, in fact, yeah, this is one reason. Yeah. Okay. Okay, the reward function is quite easy. So we have 4 variables which we want to control, which are included in this first part in the tracking reward. And we also penalize the movement and change of our actuators to avoid oscillations. So if you don't do this, sometimes the valve starts oscillating, which of course you really want to avoid. So you have this actuator reward, which just takes the change of the valve position from 2 time steps, and you just penalize it. It's a bit of a problem because sometimes you need large changes to change the operating point, but you also penalize it. So if you penalize it too much, the agent might just stay in one point and say, okay, I don't care if your tracking reward is too large, I just don't want to change my valves. And the tracking reward itself, we have decided on an exponential formulation on the absolute percentage error of each component. And of course, the problem is it's a multi-objective reward function. So if you have those 4 variables that you want to control, and you need to balance all 4. So we decided on the absolute percentage error and said, okay, we want to have the same percentage error in each variable, and this nicely balanced out the reward. You have this delta parameter here, which can scale or change the shape of the reward function, and we tried it for different values, but the algorithm found similar solutions regardless of the parameter. So we decided just on one and said, okay, whatever, it will just work. Okay, now here you have the simulation model. It's Ecosym Pro. It's quite similar to Simulink, to MATLAB Simulink, where you can have like different components here, which contains equations for the combustion chamber. They are validated by the European Space Agency, and you can put them together, change some parameters, for example, efficiencies, pressure losses, and so on. And then you get this entire model. But of course, there are some simplifications, so some modeling errors need to be expected. Although we tried to do it the best we can, but yeah, modeling errors are inevitable for real systems, I guess. The simulation speed is, you need 60 seconds to simulate 20 seconds of simulation time, so it's okay-ish, I would say. It's not great, but you can still do it with this speed. And then we compared it to some experimental data. You can see here for different components, different variables, the steady state error, transient error during changes of operating points. And it's in the order of, let's say, 2, 3, 5% for steady state. And during transients, you can get larger errors of over 10%. So there are still errors in the simulation model, and now we need to make the controller robust against those modeling errors. And this more or less is the biggest challenge, of course. So we need to be able to deal with modeling errors, with sensor noise. There are some time delays due to the measurement process of the test bench. We have external disturbances maybe, and yeah, how can we make the controller robust against it? So one very popular method is domain randomization, where you change the model parameters during training. So yesterday we have seen that the objective of reinforcement learning is to maximize the expected return of a policy. And if we introduce domain randomization and change parameters, now the objective is to change the expected return over expected model parameters here. So I have here now the expectation of model parameters, which are also included in the MDP. And for Lumen, we decided on this large list of model parameters for different components like pressure losses, efficiencies, and so on. And the idea is during training, we change those model parameters randomly. So we start with a very narrow distribution of each parameters around its nominal value. And if the controller is able to deal with this model parameter variations, then we widen this distribution. And yeah, the final step is then to train with the whole range of model parameter changes.
How do you decide what range you randomize them?
Just feeling. So sometimes the component guys can tell you, yeah, we are quite certain that the parameter is between this and that range. But in the real world, they say, I don't care, I don't know. This is our component, you can look at it, you can measure it, but I can't tell you more. And that's quite challenging. And as you can see, or will you see later, this was a problem. Yeah?
Did you ever break something on purpose in the simulation?
Not on purpose, but the controller finds ways of breaking the simulation. So yeah, I forgot it. We have a penalty if the controller breaks the simulation. It gets a large penalty. And we have seen cases where it finds solutions to break the simulation on purpose to end his life. So we had an example where the controller was tasked to minimize the propellant consumption, and it found a way to directly kill the simulation, and it was a better solution for him to kill the simulation than to suffer his life. So that was not great. Okay, here are the training results. So as you can see, we start randomly, but very quickly increase our return over the episodes. And if we reach a certain threshold, we start the domain randomization here in red. And then, of course, first the controller does not know how to deal with these variations, but quickly it adopts and learns how to deal with these variations. Then we can increase here the domain randomization, the amount of parameter changes, and then at the end we introduce also sensor noise, and then hope that it can work on the test bench. Yeah.
I don't know if you mentioned, but is it an episodic task or?
Yes. So you're right. You can also you could formulate it as a continuous task because we don't want something special to happen at the end. But yeah, we formulate it as an episodic task with distinct episode length. I guess you can do both, but yeah, this works for us, so we decided on this. Okay, then after training, here we can see the performance in simulation. So in the top figure, you have the 4 variables which we want to control: the combustion chamber pressure in red, the ratio of oxidizer to fuel in blue, the cooling channel mass flow in gray, and the temperature of the fuel in green. And yeah, it really nicely works. And we were quite happy with this result. So we see that it's in the 2% tolerance band. And here we can see how the controller changes and uses the 4 different control valves for this purpose. And it's quite smooth, so yeah, very promising result. Then we added sensor noise in the simulation to test, can it deal with this? It still looks quite reasonable. We can see some small oscillations here in the valves, so it's maybe not perfect, but we decided, well, let's go. We have not more time for training. Now let's go to the real test. First, we also tested its robustness against model parameter changes. So we ran a Monte Carlo simulation where we changed randomly parameters and compared it to an open loop solution. So we took the sequence of the nominal controller from the previous slide and changed parameters, and with this fixed sequence of valves, it results in the blue area, so a very large change of all parameters, a large control error. But the controller, because it was trained with these changes, was able to still perform quite reasonable. So it should be quite robust against model parameter changes. Okay, then it was time for the first test. My heart rate was at 200. We first start in open loop, and after like 10 seconds, we activate the controller. And you will see how it went. Yep, so not great. At this point, the responsible person pushed the red button because it was too scary. I would have pushed the button after 1 second, but okay, he trusted me. So yeah, it was not stable. It did not work. And yeah, we tried to analyze why it didn't work. And we quickly found that our modeling of the valves, so how the valve responds to commands, was really, really off. And it was the first time that we used the valves in such crazy fashion. So previously, we've just used very slow ramps, and we were not able to see the real dynamics of the valves. So our lesson was, if we train the controller with a faulty simulation, it will not work in the real world.
This was in open loop?
No, this was the controller. Yeah. So open loop, here are the first 15 seconds. You can see how nicely open loop looks. So maybe we just should use open loop. Okay, but then we corrected the modeling and retrained it. So it was a very nice property of reinforcement learning. Just change the simulation model, correct the simulation model, retrain it, and after just 5 days, we were back on the test bench. They trusted us for a second time. But I think it would be the last time. So the pressure was really high. There was,
You were showing the errors of the simulation model basically before.
Yeah.
Maybe I missed it, but did you deal with those large errors or quantities?
No, but
beforehand, or?
No, in the simulation we compared the model to experimental results, but just very slow changing trajectories. So when we are doing open loop, we are just changing and moving the valves in like 5 seconds, and you don't see the real dynamics of the valves. So yeah, we have never seen the real characteristics of the valve before. Therefore, we modeled them wrong.
Difference again between open and closed loop?
Open loop is you have a predefined sequence of valves. So you say first seconds are like 20%, and then you have a ramp, and you have no feedback of the system. So you move the valves in a predefined fashion. And in closed loop, you use the feedback of the system to calculate new valve positions directly in real time.
Technically, if you just take the expectation, it was good enough.
So
But just a comment, we do this in the tutorial in the afternoon.
and in German it's Steuerung versus Regelung. So one with feedback and one without feedback. Okay, we trained. Let's go again. So much better. There are still small oscillations, but it's for the first or second try, we were really happy with this. Unfortunately, at the end here, there was a problem with a different component which triggered the test shutdown, so nothing related to the controller. But yeah, we couldn't finalize the test. Yeah.
You did take the possibility of a totally defect sensor into account. Seems to be an important safety.
Yes. So these are questions of the future. So currently we are just using one sensor. If this sensor breaks, there's a big problem. Yeah.
So you have a smoothness penalty, which depends on
Mm-hmm.
how did you scale that in relation to performance?
No, nothing really scientific. So just try to change it a bit so that it's not oscillating in the simulation. But I guess you should spend more time finding the best ratio of performance and smoothness. But for us, it was more or less an engineering approach to just get it to work. Okay. Then finally, we asked, why did it not work as good as in simulation? Because, well, we did domain randomization, we had noise, so it should work as expected. So we took the valve sequence of the experiment and ran it in simulation with model parameter changes. And then we compared the simulation with this like area of domain randomization. We can see that most variables here are at the boundaries of the simulation. So the real system behaves still different than the simulation. So even we are using domain randomization, the domain randomization does not really cover the real experiment. So we are training on a simulation which is slightly different to the real experiment. And yeah, we know reinforcement learning neural networks, they can't really extrapolate. So yeah, that is maybe one reason why it's not working really as expected. Yeah.
So what did you change between the first and second test exactly? Do you give penalty for oscillation? Or just try to simulate the real
So we did not change the reinforcement learning setup, we just modified the modeling of the valves. Which shows you need to have a proper simulation model, otherwise you can't learn the real system. Maybe you are lucky and it still works, but you just can't guarantee it or show it in simulation that it will work. Okay, what are our lessons learned? We have seen it can work, so it can offer some large advantages for the future. In simulation, it's often quite easy, but the challenge is to go to the real system. When we tell people we want to use reinforcement learning, they are quite happy if we tell them we use reinforcement learning offline to generate or to optimize a problem and then give them the results and they can check it and program it themselves. But if we want to use it online, people are quite scared. I'm also scared. Okay, domain randomization can be good, but you still need a good model, and the simulation needs to be or needs to cover the experiment for this. And it's really crucial to go deeper into stability, robustness, how to test a controller in simulation to show that it can work in the real world. For this will I will skip. We are looking into further topics. So in terms of end-to-end reinforcement learning, ignore this figure, it's for the next bullet point. We have a student on safe reinforcement learning and he's studying, can we find out, like in an out-of-distribution detection way, can the controller tells us, yep, we are inside my training domain. And it can give you some uncertainty values, and if the neural network says, nope, I have no idea what I'm doing, I'm very uncertain about this experiment, about this system, we can switch to a backup strategy. We want to use different algorithms, of course. For me, one really interesting approach is to combine reinforcement learning with real, like classical control approaches in some hybrid approaches. Here you can see the simple solution maybe. You use classical PID controllers and only online optimize and change the PI and D parameters with the reinforcement learning agent. So people trust PID controllers. They can give you the range of the parameters, and then you can just change them in a small area and maybe optimize the performance a little bit. And it's not maybe the coolest start, but it's a start where people trust you. And we have to develop a controller for a startup in the next years, and we maybe will go with this approach. Yeah, we need a real flight controller and real space hardware, so this will be a very interesting project. And yeah, if you are interested and if you like rocket engines, the simulation model, we are allowed to share it. So if you have a cool algorithm, maybe a cool approach, how to control it, we can share it. It's in a gym environment, so very easily exchangeable. And there are more test campaigns coming in 2025 and 2026. So maybe you will be at the test bench in 2025 controlling the engine. Okay, that's my last slide. And yeah, thank you for...
Yeah, thank you, Kai, for your talk. I'm coming just so they get on the microphone. We had a lot of interesting questions. Are there any, maybe we have time for one or two more questions?
What is a section, like a problem, you think or you know that in the future only LL control can actually achieve it and not simple PID controllers?
What part or what section of rocket engine control can only be solved with reinforcement learning and not with simple PID controllers, was the question, right?
Yes.
Yes. So one part is, for example, how to handle faults. So if a sensor breaks or if your valve behaves in a different way, it's very hard to cover all these aspects with simple control approaches. You need different controllers for every scenario, every case. With reinforcement learning, we might just be able to include more sensors, introduce faults in the simulation, and the controller will learn if this fault occurs, I will just take another sensor, or I will adapt to the now changed system. This is one example which we imagine to be very good for reinforcement learning.
Did you also think about or incorporate data from real experiments into your simulation? Because source of data critique is off policy, right? So if you have a lot of data, you maybe could do something like that.
Yeah, this would, I guess, be a dream. So we have some test data, I think now 10 tests. One option is to just use the offline data, but we can also imagine to have like 2, 3, 4 tests where the controller can fine-tune itself on the real test. So like fine-tuning on the experimental setup.
Yeah.
These are options.
But is the test data also available?
No.
Yeah, maybe.
Yeah.
No.
Only part of the project, if a sensor is gone, to use another sensor or to try to simulate the lost sensor with other sensors?
You're covering all topics of our research. So this like virtual sensing approach, yeah, we had a project with the Silicon Austria lab where we looked into virtual sensing, and I think it's also a very promising approach because on real flight engines you need to limit your amount of sensors. You can't have every sensor like twice because of space and weight. So yeah, replacing sensors with virtual ones could be also interesting.
In the end, did you benchmark it against the naive approach from the 70s?
Yes and no. So we benchmarked it against a model predictive controller, which was developed by colleagues from Aachen. And the reinforcement learning approach resulted in more aggressive and more precise control results. So the neural network is able to change the system quicker, is also better in dealing with constraints. But the MPC, of course, is more robust against everything.
Okay, maybe these two questions, and then we'll move on to the next speaker.
Yeah, you were mentioning that the PI control was done with like two decoupled PI controls, the fast and the slow one. Did you also check if your agent basically can reproduce such a behavior also on different time scales, different time domains?
Nope. I mean, for this setup, you would need 4 PI controllers. And I think 4 in the same system will result in quite large problems and fighting of all those 4 controllers.
Just curious, how many people work directly on the project?
Okay, me on the controller. And the whole project, it's like 15 people. We had a budget of like 10 million. And one test day here is 20,000 euros. So that's the scale of the project. But now we got 2.5 extra millions from the German government to develop the engine further into a flight-like version. So a lot of money to spend. Last one.
Yeah.
What is the control bandwidth actually of your agent? So how fast can you control? How fast is the feedback?
So the valves are quite slow. So the valves need 1 second from like totally closed to totally opened. We decided on a control frequency of 20 hertz, but just from like a neural network perspective, we tested it on like real space hardware we could run with 100 hertz. And people from OpenAI, they showed that they can control a tokamak reactor with 1 kilohertz. So that's, I think, one of the largest benefit of reinforcement learning, that the neural network is super small. Okay.
Do you have one question, Simon?
Well, I would have so many comments, but you are not leaving soon.
No.
I was going to say, we've got a long coffee break after the next talk. where we can keep going with the discussion, because I think there's a lot of interesting points.
proposals.
Yeah, so thanks again, Kai, for the awesome talk.
Like this? Is that fine like this? Or should I do it?
As long as it holds,
Yeah.
Yeah, so our next talk is from Michael Sommer, when I hopefully pronounced that correctly.
Yes.
He's a researcher of AI and cybersecurity at UNAM Research. His background's in theoretical physics, and now he's pursuing a PhD in technical computer science, I believe.
Yes.
And has worked a lot with reinforcement learning, and we'll talk today about reinforcement learning in cybersecurity. So thanks, I'm looking forward to your talk.
Thank you. Yeah, I guess I've already been presented. So I'm Michael Sommer, working at UNAM Research, the Digital Institute in the Resilient Network Systems team. My main focus is on one side reinforcement learning and applications in cybersecurity, but also other machine learning applications. And what maybe first as a start, why I started with reinforcement learning is because I find it really cool to study how digital systems learn, I guess. I think in the DNA of a physicist, there is also a component that you're not only satisfied with statistical fitting of nonlinear functions, I think. So you kind of want to go a little bit abroad and maybe get some bigger correlation effects that are more causal or something like this. And I guess that's how my fascination started for reinforcement learning. And then actually, that's also when I was thinking about what I should talk about today is I got in touch with Andy Windisch when I was kind of starting out with doing reinforcement learning problems. And I started to come in contact with him because usually in the lectures that you have and in the courses, you usually start with some Atari, some standard environments, you train some algorithms, and this is really cool. But then after a while, you kind of start to think yourself, yeah, but I wanna develop my own environment. I wanna do something. I wanna give myself a problem and try to solve it with reinforcement learning. That's how we came together, and that's also something I want to talk today a little bit about and share my experience about this, because you have kind of, I think, first of all, you need to define a problem, and what is very important is the problem really useful to solve with reinforcement learning? What are the criteria? I want to share with you what I think, what I met, the criteria that I found out are good indicators to make it worthwhile solving it, but I always also invite you to share your experience, because I saw from also the social event yesterday, there's lots of people that have also a lot of experience. So what I want to talk to you today is, first of all, what is a problem that you can solve with reinforcement learning? So you have a subject matter component usually. So kind of you usually, or not always, I think this is also a little bit in the DNA of machine learning, that you sometimes solve or often solve problems that you're not an expert in subject matter wise. Then you need to question yourself, is the reinforcement learning framework applicable to the problem? And then you usually start off with a minimal problem that still captures the whole the DNA or the whole essence of the problem that you want to study, but it's still a minimal version to start with. And once this is said, you kind of start to think about it in a more implementation-like way. So you usually create a reinforcement learning environment, a customized gym environment usually is I think the standard API, and I will show you how I did this with the problem that I want to talk today. And then you have several challenges. I named a few there that I faced in the project or in the use case that I'm currently working on, but this is just a few implementation details. Before you actually start to fine-tune algorithms and stuff like this, before you actually can fine-tune and everything to set up the whole problem and define it and get it ready to really work on it. Okay. So the use case I'm working on is a quite famous use case in cybersecurity, penetration testing. I think the word or the term ethical hacking is a little bit more popular. Penetration testing is actually a little bit broader. So this is the whole life cycle, so to speak. What you basically, you hire a professional and he tries to hack your organization or your network that you have. Then he writes you a report, and based on he tries to find the word that you should not pronounce in public, so the V word. What you kind of try to, by finding out the soft parts or weaknesses of your network, you try to improve it. So this is roughly the use case, and this is applied in the project that I'm, maybe I can go, sorry, so this is the project, sorry that the sequence was not right. This is the project I'm working on. ResILMesh is a European Horizon project with a big consortium where the goal is to make cyber physical or actually electrical grids, smart grids more resilient through different types of applications. One side, anomaly detection, I'm working also on this, but one work package 6 in this project is dedicated exclusively to automizing pen testing with reinforcement learning, and this is what I'm working on. So you basically try to hack into your, we have a partner from Finland that is building up a cyber range. So this is already something more than the simulation. So you have real IT components, real system, but not the real system. And you try to hack into the system. So this is, can I go back? Yeah, nice. Okay. So, okay, the first thing, so we kind of understood pen testing, and let's now try to understand if pen testing is really a good or is a plausible candidate to be solved with reinforcement learning. This is just a quick reminder. I think everybody knows that quite well by now, but let's go through it very quickly. So the reinforcement learning setup, we have an environment with an agent that performs actions and gets rewards. So we need to define this kind of, to have a Markov decision. Is there a laser also? No. Okay. So to have a Markov decision process, we kind of have these tuples. We have this sequence of state actions. If you have also stochastic components, some kind of probability between the states, and you get the reward back for the action that you performed in the state, and then the environment gives you back the next state. So the question is now, penetration testing, is the reinforcement learning framework applicable? And I mean, yeah, I think it is, because otherwise I wouldn't be here. But let's break it down. What could be possible states in a network for the network that we can try to penetrate? And we can describe the network topology in an environment. So we assign, we define a vector. We'll have a look to that in more detail in a moment. But we can kind of define the network and the nodes that you have in a network as an environment. Then you can kind of give the nodes some information. You have an operating system, software's running on, and so on and so forth. So you can kind of define an abstraction to the real environment that that has a sense in the sense of reinforcement learning environments. Then in terms of actions, you can also define them. You can scan the network, for example. There's lots of tools out there that real pen testers are also using. So you kind of try to, because how pen testing usually works, you have a professional and he has not really much information about your institution. Also, he starts to hierarchically doing actions and tries to penetrate your system sequentially. And so you have network scans. Once you discover there is a node, this is the node, you can kind of try to infer some information about the node. What is the operating system running on there, some kind of software. Once you have this information done, you can start to think about how can I exploit this node. You can try to escalate your privilege, and so on and so forth. And last but not least, obviously, you also need a good reward signal, because reward, I always try to remind people, because the rewards is actually the thing that informs your neural network. So you don't have any kind of supervised learning. You don't have just examples, but the reward is, in the end, giving you the learning signal is trying to optimize your policy. And in this case, you can define it, because you start with no information. Once you discover nodes, you give a reward. You can make that proportional. Once you discover information about the nodes, you have successful exploits and so forth, so you can define that. And then I don't want to spend too much time on that, but maybe this is also, if you want to use that later on, if you really want to solve. This is a list that it's by no means complete, and it can be an endless list what are valuable criteria for a problem to be fulfilled in order to be a good candidate for reinforcement learning to be used. But these are some that I kind of always came across when I solved my problems. I think a lot of them were kind of already were part of the talk before, that you can have kind of the problems of time correlated reward signals. This is especially if you have physical simulations, a problem, so that you kind of have a mismatch in the actual feedback and the actual action performance, especially when you have such systems where time is very critical. Then you need to have an ability to simulate your environment very well, as we just saw. This is a very common problem. Then you need to have a clear objective for optimization. So kind of you need to have an optimization problem in the end. Otherwise, reinforcement learning is maybe, because you always have to think, if you don't have that, you already saw it now, reinforcement learning. What I try to tell people, reinforcement learning is for me one of the coolest things on earth. But please never force it on a problem. So this is kind of the message I want to give. So the first question, I think this should have been on the first slide. You need to ask yourself: is there a way to solve the problem, even if it's complicated, very well in a rule-based way? Then it's kind of, I wouldn't force reinforcement learning. And then there's also lots of problem out there where there is a lot of classical optimization techniques like heuristics and so on that have been studied over the last, I don't know, decades. And usually it's really hard to outperform them with reinforcement learning. I don't say it's not possible and you shouldn't try it, but this I think you should keep in mind. And then the last thing in the use case that I'm working on, or we are working on at the moment, is already quite critical, because obviously ethical hacking has a big ethical component. So you kind of, given you kind of really train a very, very good agent that can hack into organizations, you really need to think how you make that public, what are you going to do with this agent, and so on and so forth. And also safe to explore if you really want to do a real world tool, and this is actually the aim of our project. You need to obviously think also, if you want to hack into a real organization, you need to be sure that this is done safely. Okay, we have that. Okay, so let's now, what is the time? I think. Sorry for that. So let's now think of, we kind of went through this. We understood that our problem is subject matter-wise, and in terms of reinforcement learning framework, we can apply it, we can use it. It's a cool problem. We can study it. Now we need to define a minimal problem that captures the essence of the problem we want to study, but is not too complicated unusefully. And in my case, this was, you kind of need to have, for penetration testing, you have a SUT, stands for system under test. So you need to have a minimal network you're going to train your reinforcement learning agent on. And then in my case, what I defined is, this is very practical. So you kind of have different layers. One layer interacts really with the system. So really executes, for example, command line tools. Then you need to kind of, this is very tricky in this example, because due to this interaction with the system under test and the use of tools, you get a lot of unnormalized data. So you need another component that takes care of normalizing the data to map it to the abstraction that you have in your reinforcement learning environment. And then obviously the reinforcement learning agent needs to perform actions, so you kind of need to close the loop back. You need to kind of have the abstract action needs to be converted into something executable, and then something on your system, on your real system, works. Are there any questions so far? Please stop me when you... Do I still have you? Okay, nice. And this is our minimal setup. This is some kind of cyber range, so to speak. You have this is a Docker setup. So every node corresponds to a Docker container. They are orchestrated by a Docker Compose. It is from one of our use case partners in the project. This is from a robotics company. So you have kind of in the robotics use solution, you have in the robot container, you have a simulation of real robots. But the part that we are interested in is actually more than a simulation because you have real containers communicating to each other. We are not trying to exploit the robots at that point. So it's more like on a network level, and for that it's actually already more than just a simulated network. Okay, and then so the first thing, we need to create a reinforcement learning environment. And the usual standard API that is used for that is Gymnasium. I don't know how many of you have already done a customized gym environment. Can you raise your hand? Okay, that's actually quite some people. Yeah, cool. So gym is a Python API where you can that really well aligns with the reinforcement learning framework. And what you have there is you define everything that your agent needs to know and needs to be defined in the environment. So what you usually have, you need to define the observation space, the action space, and a few other components you need to, and then you usually have the structure. You need to have at least, I think, 2 functions you need to have. One is the step function that defines what happens based on an action and in the current state of the environment, what happens. And this is what you can see there. And this function needs to, by definition, in order to be inherited from this gym environment class, you need to have a step function that takes in an action and gives back the state of the next state, so to speak. So what happens to the environment when the agent performs this action? A reward signals, then you have 2 flags. This has also changed. I don't know if somebody was working with gym format, the former version was called gym. There you didn't have the truncated, so you need to, in order to use the newest version of all these algorithm packages like, I don't know, Ray or stable baselines and so on and so forth, I highly recommend to transition to this Gymnasium fork now. And then you need to make a few adjustments and then everything is compatible again. And then you also have a dictionary info where you can put information you want to put. I was also using it and we will see that in a moment. Okay, yeah, and so in our use case then, we saw that the environment before, we have 5 nodes in our network, and this is represented by this array that you can see there. So the observation space is defined as a dictionary space. This is more just kind of to make it a little bit more human readable. In the end, it's just tensors. This is what you can fit into a neural network. And -1, you need to kind of apply a padding technique because at the beginning you need to kind of pad them out and give a value into the state in the observation space or the states that do not contain any information about the system. So you start with this padding. Then you apply an action. You have 1 and 0. We'll have a look on the next slide on what this 1 and 0 means. Then you have a state after the action, a reward, done, false, and everything that you can see on the right on this step function. And in this info, you can also see here, I will explain that in a second, and this was an invalid action. Because obviously, as we already understood is, you have a lot of actions available in penetration testing, but you cannot at every state you are in the actions that you can perform in a given state depend on the state. So you cannot exploit the node when you not have discovered it, when you don't know anything about the node. So you kind of have this hierarchical dependency in the actions. Good. Are there any questions so far? Any comments from people that already did gym environments? Yeah?
If nobody says.
Sure.
So in the step function, the truncated output is very important if you think it through in some cases.
Mm-hmm.
Just to mention this, so they didn't introduce it for fun. It might be the case that your episode is, for a technical reason, stopped at one point and you don't want to tell the algorithm this is the end of the episode, then you would use the variable trunking.
Which in this use case is super valuable because you're using a lot of practical tools where a lot of things can go wrong. And you kind of need to integrate that into exception handling, but we'll have a look on the next slide about what I call interaction challenges. And this is very valuable. I think also this is very valuable that they introduced this. Thank you. Okay, so now let's think of, we have kind of this architecture, we have our system under test, we have layers that interact with the system. So in this world, this is real action. So you kind of really have, at the top you can see this is a defined Python function that really executes a command in your, we can go back. If you think here, so you kind of, your access point to the network is you're in this container, in this attacker container, and within this, the terminal of your attacker container, you execute some command line tools. And this is what happens exactly here. So Nmap is a very popular scanning tool, very widely used in the whole field of cybersecurity and beyond. And what it does, it gives you back some kind of these XML files with information about your system. And what you can see here, for example, we discovered, this is just an Nmap scan, we discovered an IP address, as you can see here. And then there's lots of other information. And then you can also, once you discovered this IP address, you can try to think of how to get further information about the specific node and so on and so forth. And so now the challenge that we have is we need to find a way to represent this, what happens here in this real world, to kind of find an abstract way to, I say it very directly, we need to kind of define an array or tensor in the end, because this is what we can fit into neural networks, and this is how deep reinforcement learning works in the end. And so we need to kind of define this. And what you do is, for example, we saw this is one of our state space. Let's start with the states before. So we have this dictionary just for human readability. We have the first array contains information whether the node has been discovered. For example, here the first node, the second, the third, the first and second, they have been discovered. The other one we don't know anything about them. And then we have also information about the operation system. So according to every node, we can kind of define what could be this information. And the problem is also always you kind of need to find an abstraction or some kind of embedding to make also the information available to the agent. We were discussing with the colleague this morning or also yesterday afternoon about one of the use cases he's working on. And the thing is, you obviously can abstract very much in the sense of reinforcement learning, but then you need to also be aware that your agent is really kind of in a dark room, And this is especially a problem when you simulate environments. Then you get a high simulation bias in your thing, because you kind of start to really make a lot of assumptions of the nature of your simulation. And the same is for actions. This could be an action that you apply, and obviously the most straightforward thing you would do in this case, you can define this as discrete actions. There is no problem. Like applying an Nmap scan can perfectly be abstracted to a 1 or a 0. There is no problem at all. You can applying a scan to your node number 3 is perfectly a discrete action. The problem that you get, and I don't know if you have enough time then afterwards to talk about this, you get your action space blows up. So when you start to, and when you check the literature, what I did when I started with this project, I think the absolute maximum for similar use cases, because this penetration testing with reinforcement learning has been researched quite a lot, is the absolute maximum is 100 that you can get. And this, I think, is already a lot, and there they already try to make the Q learning, they have evolutions of the Q learning or deep Q learning algorithm, and stuff like this. So I think 30, 40 is for a practical use case, because we really want to also do something that can be applied in practice, is already a lot. And then you limit yourself a lot to in terms of the network size that you can actually scan. And so an alternative approach to this is to formulate it as a continuous problem. So you kind of get this vector. You have the first entry corresponds to the nodes, and the second one corresponds to the action that you want to apply. And this obviously is much more stable, and there you can, in this kind, the algorithms like PPO, or we had SAC, soft actor critic before, they can, in this way, kind of, it would be a problem if you blow up the dimension of your vector, but as long as you stay within reasonable dimension of the vector, within the values, you can vary them a lot. And so this is what you basically do. You define not the discrete action, but you kind of have a window within this action has been will be applied, and you can do that very nicely. What's the time? Okay, nice. Okay, nice. And then one thing I would really like to talk about is, because I think what I see is people that there's different phases, I think, when you start to approach reinforcement learning. First, there's this phase where everybody is super excited, we're going to solve every problem of the world with reinforcement learning. Then kind of there gets a low, and then it kind of balances to a more reasonable expectation of what this technology can do. But what I really want to underline is usually people do not focus enough on the reward mechanism, and this is really, really important. People think, yeah, they kind of say, okay, we get the reward, this more or less corresponds to the problem, and they immediately start to try different algorithms, they start to hyperparameter tune, and so on and so forth. And I really want to encourage you, and say this again, the information of your problem is in the reward. So if you think about it, even in the state-of-the-art algorithms, they all use value functions or advantage functions, and there you, in these value functions, you have an incorporation of the reward. You just try to make sense of it in a time correlation sense, but it's still the information comes piece by piece from the reward that you get back from your environment, because all the rest is fixed. And what you can see here is, we were discussing about it, not every action is valid at every state you are in, because you cannot, as I said, you cannot exploit a node when you not even know that it is there. And so what you kind of, the first goal that you kind of have with such an agent is that he starts to learn what are valid actions in what state. And you can do this by penalizing slightly the agent when he does an invalid action. But the biggest issue that you have, you still in the end want to solve the problem and find the optimal solution, because otherwise this makes no sense, right? So you're doing this for getting the convergence above that you can see there, but in order to come there, you kind of need to know the valid actions. Obviously, you could overrule it in a rule-based way, that you say this is allowed, this is not allowed, but in the end we want to do something a little bit more intelligent and won't really leverage the technology for a real-world problem, and so this is what I tried to do. And what you need to think about is you have kind of this, you need to reward shape, so you kind of give at every time step, you give a slightly negative reward. But the question that you need to ask yourself is, what is the right magnitude of this negative reward in order to penalize the agent in a right way that he still learns something and still can reach the optimal solution? So this is the issue. And I've done this a few times, and what you need to ask yourself is, first of all, that let's say it like this, the easiest way to define this is you ask yourself, what is the negative reward at every time step, what is the whole episode length, and then what is the maximum cumulative negative reward that you can get. This might not apply to every problem. Even here, you would need to really resemble it. You need to think about it a little bit more into detail, because there is only a limited amount of invalid actions in the end, because there are also valid actions, because otherwise we could not solve the problem. But this could be a first attempt, and this is how I would try it for the first time. And what I can see here, for example, if you give -1, or maybe first of all, you need to set the scale. So what is the maximum positive reward? And here it's about 8, I think, because we have an environment of 5 nodes. We can discover all 5 nodes, and I think for how the system is designed, you can get also operation system information of 3 of the nodes. So 8 is the maximum score that you can get when solving this problem. If you assign a 1 for every discovered node and every operation system information discovered for every node. And so you need to set the scale, and then you need to think about how could you define your negative reward for invalid actions. And for example, there's a few examples there. If you give -1 for every invalid action, kind of you see the agent doesn't learn anything. It just remains this like a random agent. It doesn't do anything. If you use -5, you can see there at the beginning he starts to learn something, but it's by far not the optimal solution that he can learn. And then I kind of tried to make it also a scalable solution. I do the maximum episode length times -8, so the maximum, if really, this does not really apply because there's also valid actions, but in this approximation, at every time step you get the the negative reward for invalid actions, you get the -8, and you see this works out nicely. But the point that I want to make is, if you think about it, -5 and -27, there's not a really big difference between them. And I can guarantee you, if you use -5, you can hyperparameter tune until your pension. You're not gonna get the optimal solution out of the problem.
Maybe just a comment. We played with this in the tutorial.
Yeah.
So very
cool. Yeah, and then there can be, obviously, for example, this is not always so trivial in this example. For example, I also did a numerical simulation once for this lunar lander example. I was studying that because I'm a physicist, did a lot of numerical simulations, so I built a real numerical simulation about this. And the issue that you also have is when you start to have, for example, if you have a numerical integration, and you vary you give at every time step you give a negative reward or a possible negative reward. This is done, for example, in the lunar lander. You slightly penalize it for waking and stuff like this. And if you then vary the integration time that you have, you also vary a lot the potential possible cumulative negative reward. And this has a big impact on your simulation. And if you think then of a two-dimensional grid, there it's not so trivial to think, if you have this lunar lander flying, it's not so trivial to think what is actually the maximum possible negative reward. So there you need to kind of think then. What I tried out is I used a random agent. I did a lot of random agents, and you kind of scale it. I also related it a little bit to physics because this plays a role if you kind of use physical parameters. But what you would use is, I think a good start is try a random agent and see what is the average negative reward he gets, and then you can start kind of thinking about distributions and how this relates to each other. Okay. Yes?
What do you think about scaling the reward with the integration step? So it can be so that you scale it with the number of time steps in the episode.
Yeah, the thing is, you have nonlinear effects in there, and this didn't work. This is why obviously this would be very similar to what you have here. Because the time step, and if you leave then the episode length, you scale it with the same absolute time scale, but this didn't work. So you need to have something more, because you have kind of this, you need to have a concept that kind of takes care of the nonlinear effects in your system. But sorry, this is not related to our pen test use case. Yeah? Yeah?
I have a question about the action. So you use a multi-discrete action, I think.
Yeah.
And you have 2 dimensions?
No, this is, you have kind of this. We can go back. This you have, yeah.
So every choice, every discrete combination of
Yeah.
these two
Yes.
are a different tool with different parameters.
Yeah, the thing that I did for this is why it's defined the number of nodes in the system plus 1, because the plus 1, if you want to then make this a generalizable solution, the plus 1 would always be an action that you apply to the whole network, because this is how you would start. You would start to do a network scan and see what is the real network about. And so there you don't need to really have different node information. So this would be the plus. That's why it's plus 1. And then the number of actions, these apply all to the different nodes. Yeah, and we also try, because we in our group we have a discovery tool. So the idea is then ideally to make this process to automate that. So we have a tool that discovers the topology of a network. And ideally, what we want to do is that we at least the setup of not the training. This is really hard to. I think most of you that do reinforcement learning, automating the training process is a wish of all of us, but in practice usually not so easy. But at least these tedious things, if you try to define it in a scalable way, that you can by varying just the nodes in your network, that you can automate it by the tool that we're using. Yeah. Go ahead.
Excuse me, like usually in pen testing simulations, let's say that to detect an abnormal behavior of the network, usually like even classical neural network can be trained to classify a behavior of the network as normal or abnormal,
yes.
Let's say, condition. Like compared to this case, how can reinforcement learning be applied to be a more, let's say, effective in this sort of situation?
No, but this is a completely different use case if you think about it. I mean, I'm also doing that a lot. Like this is like the difference is the use case that you just described. You're inside the network and you try to defend from attacks from outside. The use case here is actually the opposite. So you try to attack from outside the network. You don't know anything about the network, and you want to attack it, and by this process, you want to try to see where the network has weaknesses.
Okay, got it.
Okay? Yeah, please.
Sorry, I'm kind of new to this field, but you
Yes.
distinguish between this reward shaping and hyperparameter optimization.
Yes.
But isn't this also a hyperparameter?
I think that's more a philosophical question, to be honest. But it's not the hyperparameter of the algorithms itself. So you usually you define your environment, and once you define it, so the environment consists of this. So the environment consists of this. So you have the environment defined, and in the environment you need to define always these tuples. So you have a state. The current system, for example, we don't know anything about any node. Could be an example for a state. And then the agent applies an action. And then another state comes back. For example, as we have seen, we know now there is node 1 and node 2. And we get also reward from the environment back. And this is actually the thing what I was trying to do today is to make you familiar, or to show you that you need to really think well through this before you start to think about what kind of algorithm to apply or what hyperparameters inside the algorithm. Because what the algorithm tries to do is to solve this problem in an optimal way, that you can this agent gets a brain that optimizes that he after a while starts to understand, now I'm in this action, and this is the optimal action to take in order to get the most cumulative reward. So if you then play until the end of the episode, that if you sum up all the rewards, this gets a maximum. This is what the algorithm tries to do.
Maybe I have a comment, because the reward shaping is not, so we have the MTB, and the reward function is part of our problem definition. It has nothing to do with the algorithm afterwards.
Yeah.
So we say we have to design the reward. This is the reward design.
Yeah.
And the reward shaping generally refers to the fact that we try to make the reward in a way that the algorithm works better.
Yeah.
So it's in between a hyperparameter and not a hyperparameter, but mathematically it's part of the MTB and not part of the agent.
Yeah, because the issue that you usually have, that as we have said, that the reward gives the information to the algorithm and the networks, And in most real-world problems, if the reward function is not defined by the nature of the problems. I mean, there are a few problems. For example, I once did a trading bot for portfolio optimization. There you have really intrinsically from the environment, you know, after the next times that if you have earned money or not. So there you have, by the definition of the environment, you can really easily define a reward function. But in most real-world problems, you kind of need to give some domain knowledge of the environment and think it smartly through in order to make this happen. Yeah.
Would you say then that the reward function can be optimized in general, or like yesterday you
Yes.
mentioned that's the definition
Yeah,
of parameters that you can
absolutely, absolutely.
generally.
And yeah, please.
Because you mentioned it when you do this in the beginning, including the episode length to penalize.
Yeah.
And you said sometimes it works and sometimes also you cannot just integrate. So it plays a crucial role then in the training, how the reward function looks like. And usually some people tend to normalize the reward function, for example, but we don't have this issue. Yeah. But the reward function tells you what to do and how to do it. So both things are included in this.
Yeah.
This is important.
Any other question, comments? Yeah, then I thank you a lot for your attention. It was a great pleasure. Thanks for having me and hope to come back soon. Thanks a lot. Yeah. By the way, if you, sorry, just 1 second, I need to jump to the end. If you want to get in contact with me, this is my LinkedIn. I will be very happy to discuss with you. As I said, not only reinforcement learning problems, I'm also actively in other, especially in deep learning and autoencoders. I will be very happy for that. Thanks a lot.
Perfect. Yeah, thanks very much. Now we have a coffee break. We'll start again at 11:45, so please come back maybe a little bit before so we can start on time. And you saw, I forgot to mention, we just switched up the order of the talks today because there was the delays with the train, so not to be surprised. Perfect.
Thank you.
Tasten drauf. Ja, so, genau.
Okay, welcome back everyone to our second morning session. Our next speaker is Anton Fuchsjäger. He's from Enlight AI in Vienna. He's maybe from the minority of us. His background is in AI. He studied in Edinburgh and is since 4 years head of AI at Enlight. So looking forward to your talk.
Thank you. Yeah, first and foremost, thank you for inviting me. I think it's a great pleasure to give some insights in what we're doing at Enlight AI. And today I want to tell you about mainly the work we did in power grid optimization in the energy sector. So maybe a quick outline. So first of all, I'm going to give a quick introduction about Enlight AI, what we do and how we ended up in power grid optimization. Then I will talk about the problem itself and why it's such an interesting problem for reinforcement learning. Then I will present the solution, or like one solution we came up with. And then the next point is how we can actually apply this method to the real world and a proof of concept we're currently working on. And then finally, there's some room for questions as well. So let's get started. Enlight AI, in a nutshell, is a deep tech company based in Vienna. We are roughly about 20 people, where 6 of those are working in the power grid optimization reinforcement learning team. And there are 3 main pillars at Enlight AI. So one big one in the middle is detect. This is more like a classical AI project where it's about like detecting street cracks and signs and things from street data. Then at the bottom we have Maze-RL. This is an open source reinforcement learning framework that we built mainly for applied reinforcement learning. So the idea here is that we found that the frameworks that were publicly available are very focused on research, but when it comes to applying it to like actual problems, they all were missing bits and pieces. So we started, why not build it ourselves? And then from there we moved to energy, and this will be the main focus of the talk today. So maybe a quick track record. As I mentioned, we built this open source reinforcement learning framework, and then we kind of like sat down and we're like, how can we apply this? How can we show the use cases? And found the Learning to Run a Power Grid challenge, which is a challenge organized by RTE and TenneT, 2 major TSO, transmission system operators, participated in 2021 and won in 2022. And from there, we also wrote a paper that got published at the Europe's workshop, also won the Austrian State Award for Innovation. And since 2023, we're actually working on a proof of concept with TenneT, which is the transmission system operator of the Netherlands, and they also do a big part of the German grid. Parallel to that, we also have part of a big consortium project by the EU Horizon grant called AI for RealNet, where we also work with grid operators as well as railway operators and air traffic management operators. So the idea is to find like build a common framework for critical infrastructure. And also we kind of like exploring how we can test our methods and our approaches in the more local scale, so on the distribution system operator level with 2 local Austrian DSOs. In 2024, a new AI Horizon project will start, I think, next month, and also participated in the Free Electrons Challenge, which is a startup challenge for the energy sector specifically. Right, so quickly our vision, but I'll go to the problem, which is the more interesting one. So when it comes to the power grids, and this is always on a transmission system level, so meaning like the very high voltage power grid. So this is kind of usually on a country level, where they have to kind of like manage the interconnections to other countries as well as like the power plants, and their loads are usually like smaller cities or even big cities or big industry. And this is facing like critical challenge at the moment because of the expansion of renewables. There's much more change in the network, in the production. There's higher electricity demand, which results in instability of the grid, higher operational costs, higher CO2 emissions, and this is obviously problematic for two main cases, the operation planning, which we'll focus on today, and the long-term planning. So, quick intro. This is a very simple power grid. Here we see that we have a few generators in blue. So these can be like wind, solar, or fossil fuel generators such as gas or coal. On the other hand, in orange, we have the loads, which is smaller cities, industry, or interconnection to other countries. And they are all connected through power lines and substations. And what we see here is a congestion. So this means that one power line is carrying too much load or is utilized too much. And this is problematic because on the one hand you have losses because they are not designed to carry that much load. On the other hand, if it keeps increasing, the power line can break or melt. So this is like, even the TSOs are actually required by law to kind of like not have congestions in that way. And the question is, how do we solve a congestion like this if it occurs? So the standard approach is called redispatching or curtailment, meaning that on the one hand, I curtail the wind park on the left-hand side and reduce the energy, or basically pull the brake there. And on the other hand, closer to the load, the big city on the top right, I increase my fossil fuel generator, because there I can just turn a knob and get more energy. This, of course, as you can imagine, is really expensive because I lose the energy twice. On the one hand, I have to break the power plant on the left. On the other side, I have to buy more coal, buy more gas, and produce loads of CO2 as well. To put this into numbers, so on the right-hand side, we see a plot of the energy or like the type of generators that are used for redispatching. And what we can see here, the big yellow part is all coal. And the turquoise part on the bottom is gas. So this is kind of already the major part. And then the big white section is unknown, which is, I think, quite funny. But it's basically just they bought it from a neighboring country or something, which probably is also gas or coal. And so this is, for example, for 2022 in the German network. And this, of course, directly correlates with CO2 emissions and also money, as we can see on the left-hand side, the trend of how much money is put into redispatching in Germany. And this is like already like crossing the 3 billion threshold. And this is not like the normal operation. So this is basically just fixing the problems that occurred along the way, or miscalculations in the plans, or changing weather events, all these things, which is like an incredibly large amount, of course. Right, so now I want to present an alternative to the classical redispatching, which is called substation switching. So substations on the TSO level have this capability that they have like two buses, they're called, bus A and bus B. And everything on bus A is connected, as well as everything on bus B is connected. And operators can switch elements from bus A to bus B if they want to. They can split the substation. So in this case, for example, the top two lines are put on bus B, which separates the substation, creates kind of like a virtual one, and redirects the power flow such that the congestion is solved without doing any redispatching, which is, of course, really nice. Now, the big question is, why is not everybody doing this, right? Because if there is a cost-free way of solving these problems, why not do it? The problem is complexity. And this, I want to spend a bit of time going into this, because I think it's quite interesting. So here we have like two different views of the same thing. So the split substation on the left-hand side, as well as on the right-hand side, we have it with the two rings. So the top two power lines are on the outer ring, and the other power lines on the inner ring. They are both, like all elements on the ring, are connected, but the two rings are not connected. Now, if we think about the possible configurations that we have on this one substation, we can see that each power line or element can be either on bus A or bus B. So I have 2 to the power of 5 in this case, which is 2 to the power of branches in the substation. Now we can already think of one reduction we can do to reduce this complexity, which is seeing the symmetry in the connections. So for example, topologically speaking, everything being connected to bus A is the same as everything being connected to bus B. Thus, we can always fix one branch and already reduce the complexity. If we think about the grid we saw earlier, this means for each of those substations, in 4 we have the number of configurations here. These, of course, need to be multiplied, which already gives us 262,000 possible topologies for this really small toy grid we have here, which is already like a ridiculous amount. So we introduced another reduction, which is saying that no one element, we never want any configuration where just one element is on one bus, so that there are no bridges basically, and it's like more secure, which gives us a bit more, reduces the number quite a lot, so we're already on 1,000, which is more manageable for us. This is like the other grid that we started next, like much larger. So here, this is like a grid quite often used in research literature. It's called IEEE 118 because we have 118 substations. But as you can imagine, the number of configurations we have here is enormous, like not manageable. But here we already start thinking about the agent interaction and the reinforcement learning control loop. So what actions should the agent take? Generally speaking, ideally, the agent would pick one configuration of all the configurations that are possible. But as we saw earlier, this explodes like exponentially, super quickly. So we have this reduction 3 that we say one timestamp, the agent can only manipulate one substation. So in timestamp 1, it could change any substation, and then the next timestamp, it could change another substation. This gives us, in this grid, already like 72,000 actions for one timestamp, which is already also really big. But then we also introduced a 4th reduction, which is not directly correlated to the action space, but more to the total number of topologies that are available, which is saying that we can have maximum 3 substations split, so to speak. And this is interesting, especially for operators, as we learned over time, that they don't want to diverge as far as like that far from the reference topology, as we call it here. Because the problem is like sometimes you can go to like a really good configuration, but then you might not be able to go back to the reference grid because things change in a network. It could be day, night, then the load looks really different. If there's a really strong wind, it's like utilized very differently. So they don't want to diverge that much. That's why you use this introduction, and it makes things a bit more comprehensible for reinforcement learning. Right, so why this is, so when we looked at this, we thought like, this sounds familiar from like the abstract problem description, right? We have a huge amount of actions and like even largest possible configurations of the network on the one hand, and on the other hand, we have a very high dependency of actions that I do now, how they affect the future. So this kind of like reminded us a bit on chess or Go, right? Where you have like an opening move can really influence your game. Like if you do a bad opening move and you're playing against a good player, the game is over pretty much. And that's how we thought about using AlphaZero for this. So we kind of read up and looked through the literature and started working on from the base version, and then kind of like drifted more and more towards a customized version for power grids, where we utilized like the best fitting things from AlphaZero on the one hand, where we have like from AlphaZero as well as mu0, because mu0, for example, has discounting and infinite horizon games, which is very valuable for us, which is kind of also an infinite horizon game. AlphaZero, on the other hand, is like finite always, because it's a game and you have like a finite reward at the very end. But here we have like intermediate steps, so we want to use discounting. But on the other hand, don't want to use a learned model for the simulation, because power grid simulations have been like used for many, many years now, and there's been a lot of like effort going into them to making them really fast and really accurate. So we have like a really good simulation and a really high action space, large action space. So we combined those things into building like an AlphaZero for power grids. Wouldn't be a reinforcement learning talk without the loop. So here, just to reiterate, our environment in this case is the simulation of a grid based on the network parameters and the model and the power flow computation. From there we get the state and the reward. We feed it into the agent, and the agent produces topological actions that we feed back to the environment. And then we can play this game, let the agent train, and hopefully learn something that is able to mitigate congestions much faster than any heuristic and much more accurate as well. And in our case, as I mentioned with the AlphaZero, our IL agent is not just a plain policy, like a neural network, but it's a neural network embedded in a tree search called MCTS, or Monte Carlo tree search. So it's basically a large-scale tree search that is guided by a neural network, kind of like giving intuition on what branches to explore and to expand. Here's like a nice image of how this could look like in practice. So we build like a huge amount of possible solutions, and then in each time stack pick the best one. And so the learning loop for AlphaZero then looks like this, that you do this iteratively. You produce actions with a tree search, firstly initialized with a random policy, to create expert trajectories. At the beginning, there probably won't be like expert trajectories, but they will be better than the random one. And then you take this and update your neural network with it, and then you go back and give the neural network back to do the MCTS and collect new trajectories. And this is like very simplified, the iterative process of MCTS. And so what we did for this paper I mentioned earlier was, after the challenge, we looked at this grid and tried different things. So we used it with MCTS only, or we used it with the torch policy only. And then we also started thinking about if it could be combined with classical redispatching methods in order to even further boost the performance. And there we saw that combining those two things, we were able to remove the redispatching from redispatching only, so to speak, by 60%, and while at the same time increasing the robustness by 7%, which is very nice, I think. The thing about the problem here is this is a very much a toy example. This is part of the challenge and is concerned with very difficult situations. So here, this was in this challenge, you always had to survive as long as possible, basically. And the real world looks a bit different. There you kind of like not always have these super tricky situations, but also sometimes just want to optimize a bit without going too far away. Because our agent here is, of course, highly active. It kind of like switches a lot, which is usually not preferred by operators. And this brings me to the next point. Like, what about the real world? So after the paper and the challenge, we started reaching out to operators and managed to, for like 1 year now, we've been working together with Tenet on a proof of concept where we actually look into how this technology could theoretically be applied in the real world. And there we mainly tackle this one question. This is in case a disturbance arises in normal operation. Multiple plans should be identified, generated, and presented to the human operator in order to help them make the best decision with respect to certain criteria. And here, as a side note, so a plan here, this is called day-ahead planning. So basically, operators refine their plans over time because they have like outages, or planned outages, but also can have unexpected outages. And this plan is refined as the predictions for the weather predictions become more and more accurate. And with the weather predictions, the predictions for renewable energy becomes more and more accurate. And then the day before, they try to kind of like decide on one plan that they want to do. So a plan here is basically then one day having 24 timestamps. So you can do one action every hour, basically. The grid itself, even larger than the last one. So here we have like more than 1,000 nodes, including the injections, and roughly like about 1 million switching states. And as you can see here, this already brings up new problems that I want to go into now. Mainly on the one hand, the time, of course, because this should work in reasonable time. But mainly the thing was, or the main thing was, that there is not one plan that rules them all. We don't have like one solution or one ideal plan that is better than everything else, because we have multiple KPIs. We don't have one KPI which is just like reduce the load as much as possible, but we have two KPIs in this specific case that are concerned with the actual load flow that should be reduced. But then we have three more which are concerned with the topology. So here on the one hand, we want to do like as little switching as possible throughout the day, because switching is always in the real world connected to like actually like they have to devise a sequence of how power lines need to be switched, and this is also quite an intricate process. On the other hand, they want to minimize the number of reconfigured substations, so they don't want to diverge too far from the reference grid. And finally, the amount of switching, so going from one timestamp to the next one, should also be minimized, such that it's less work. And this already becomes quite tricky on just this one side. But on the other side, we also have multiple plans. So if you think about reinforcement learning, it's usually trained in an environment to produce the best action. This means that my top action, the top action sampled, if I train it well and everything works, is probably a good action. But I can't just know, like I don't know if the next action I query will also be good, because it was never trained for this. So this kind of like brings up a whole new problem. And this is kind of like where we currently stand, and currently where the research is going at the moment, into like looking into multi-objective reinforcement learning on this one hand, or kind of like edging towards multi-objective reinforcement learning, because this of course makes the problem even more complex. Because if you consider this problem that you don't have like one specific solution, you need much more training time, of course, because you have like different variables, and the literature is also not as evolved there yet. So currently we are looking at different approaches, how to like go there slowly and steadily. The first ones, of course, are utility-based, where we look at like how can we weight the different KPIs up towards another. So because some, of course, are more important than others. But next steps will go into more like conditioning the policy on given input, such that for given input it produces specific actions in this direction. And yeah, so this is kind of like currently where we stand at Light AI in the energy sector. And it's quite interesting, because there are like a lot of problems that come up and that really need a lot of thinking and how this can be done. One final slide, then we can do questions. And this, of course, is the goal then, So basically, to have this is a demo we did that can already you can try it out even on the website. This kind of like should showcase a bit like the goal, right? So we have this could be a user interface for the operator where we have like present different plans. So in this case, the plans are based on the amount of redispatching I do. So on the right-hand side, I only have topological actions. On the left-hand side, I do nothing, and then the next one is only redispatching. And then they can investigate the different plans, look at the different actions, see what happens, look at the KPIs at the bottom, all these things. And this would be like the goal at the moment to kind of like come up to kind of like move closer to the real world operation room with tools like this that actually not replace the human operator, such as like we just put in an AI and it does everything, but rather to help the operators make better informed decisions in order to save CO2 and also money. Yeah, and finally, we're also hiring at the moment. So in case you're interested, please feel free to approach me afterwards or just send an email or something. Yeah, sure.
Do you also consider explainable or the explainability? So the operator gets 5 ideas or options. They somehow have to decide, and the reinforcement approach might come up with way more complicated solutions than they would be thinking of. So do you
Can you please repeat the question? Oh yeah, of course. So the question was if we are considering explainable AI and ways of how we can explain the actions to the operators.
maybe simplify them for the operator.
Exactly. So here, not specifically, because this is more focused now on like producing good plans, and then we kind of like more. I mean, you could frame it a bit under local explainability, such that it's such that the individual actions are can be inspected by the operator, and they know the different actions. I mean, this is the assumptions that they know the substations, they know what's happening, and they can view each action individually, look at them, and then the combination of this can be viewed by visualization, which is more local explainability. More robust ways, I would say, of explainability, such more like with explaining actions per se. This is covered, or this is something we're working on in the AI for RealNet project. So this is a bit more research focused, and this big consortium project. So we're like 15 or 20 partners from academia as well as industry, and they are, as I mentioned, we're trying to build like this unified framework for the rail networks, energy networks, and air traffic networks, and their big focus is also on explainability. Mm-hmm.
First of all, I really like the approach that you make suggestions to the operators, and in your experience, do they accept your suggestions, or at least say, "Well, that's a nice idea." I guess for them, they do not care if it's generated by AI or by some physics-based rules.
Mm-hmm.
I guess it really helps to increase the acceptance of reinforcement learning. Right? But on the other hand, have you seen problems that you find solutions that are technically solutions to your KPIs, but then the operators say, in theory this is a solution, but insert random argument why it's not possible, because you can't, I guess, cover all domain knowledge, all problems, all possible scenarios they have encountered in the past.
Mm-hmm.
It's hard to find a solution that they accept.
Yes. So quickly to reiterate the question, was like if you found problems that, or like if we presented plans that were not accepted based on outside knowledge. Right, that was the second part? Okay. So generally, we don't work directly with the operators. So basically, we work at the team at Tenet, in this case, that are kind of like working on this a project called the Control Room of the Future. where they're trying to set up something similar as I showed in the previous slide, this UI basically, in order and then have this interface where they could put in any plans. So they are working internally mainly on heuristics, and we are the outside partners who work on the AI approach. And they are currently doing tests on how the operators like the interface, how much the acceptability is for new actions. So I can't really go into detail on this yet, but hopefully soon I'll know more about it.
And maybe a follow-up question, do you think you can also use the same approach or similar approach, for example, to optimize the German train organization? Because I've seen the documentation where people are sitting in a room with their 17-inch screens, and they're manually trying to redirect trains and calling the trains, hey, please wait 5 minutes. And it's a super dumb approach for such complicated system. And I guess you could also optimize a lot with more.
Exactly. And even in this AI for RealNet project, Deutsche Bahn is partner because I think they're quite motivated to find a solution. And they're actually, I think the other problem is more concerned is similar. It's also the rescheduling, right? So they produce really good, really accurate plans in advance, but this takes a day or a week. But then something happens, like a tree falls on the train, and then they have to reschedule, and their algorithms are too slow. And so I think this would fit really well there as well, and we're currently also investigating this with this flatland environment. So if anyone is interested, I think they're planning to do a challenge next year. And this is like a toy environment for trains as well, where you can reschedule trains. And yeah, I can tell I played around with it as well. It's really tricky. I have much more respect now for the problems that there was. Mm-hmm.
Maybe a comment of this. The Deutsche Bahn hired several PhD students 2 or 3 years ago because they want to attack this. I don't know if you're aware of this or involved in this, but they are on this.
Mm-hmm.
And they don't know how to do it. So the feedback I don't know what happened in between.
Yeah.
But yeah, they took some money to really bring reinforcement learning to this problem, which is cool.
Yeah, I think so too. Mm-hmm.
An open problem that we face in my country regarding power plants is that, I also studied this a little bit, but someone told me that if some foreign agents would attack 2 of our power plants, the whole country would go into blackout because like a domino effect,
Mm-hmm.
the load will. So let's say, is there a way like adversarial neural networks that I have agents that compete with each other in a way that someone's reward is another person's loss? Does it make any sense to let AI attack AI and let me know the vulnerabilities?
I think could be quite interesting as well. Yeah. So for example, in the grid to op challenge, so this is the power grid challenge I mentioned, they used an adversarial agent in order to simulate outages, because these outages usually are mainly concerned with natural disasters like flooding or weather conditions. But in this challenge, they used an adversarial agent to attack specific lines at random points. I think generally this will be quite interesting as well going forward. But currently it's like one step at a time, right? First like the normal operation and then the outside attacks as well. Mm-hmm.
Sorry if you already mentioned it, but did you try at any point in this work to use graph neural networks?
Yes, this question always comes up. We did try it once, I think, but there were always like so many other things to try out first. So we never really got into depth there, but it's like high on the list of priorities to check this out. Mm-hmm. He was like a bit longer.
Doing multitask optimization, did you observe the problems that were discussed in the first workshop, like that the learning of concepts is sequential? So maybe the agent first learns to optimize the first KPI, then the second, then the third, or you did not observe that?
So as I mentioned now, so the question was like if we notice like a sequential ordering of how the KPIs are learned by the agent. Right? So generally, we have at the moment still mainly focused on 2 KPIs. So on the one hand, we have like the load flow, and on the other hand, the switching, which seem to be the most important ones currently. Next one we will consider is the number of substations reconfigured at any point. And so mainly the work so far has been using utility functions. So we have like, which weights up the different parts of the reward. So you have like one reward for the switching, one reward for the load flow, and you give each part of the reward a weight and then compute one scalar reward again. And there we saw, like, if you look at the different rewards while learning, you see that sometimes they kind of like figure out to kind of like switch less is good, and then they start doing the load flow optimization, and sometimes it's a bit the other way around, but this seems to be happen sometimes in this way, sometimes in the other way.
So you do observe these phenomena?
A bit, yeah.
So I guess controlling that huge system is pretty complicated, and there can appear, I guess, situations where you have invalid conditions, right? Like, for example, too many power plants feeding into a line. How do you prevent the agent to pick up invalid actions?
So we use extensive masking and have like a bit of advertising for the Maze framework. Their masking is built in, so you can specify the masking at given with a wrapper basically. So you usually have like the environment, and on top of the environment you build a masking wrapper, which actually looks at what actions are invalid and which are not. For example, a good one example could be that one power line is, for example, in maintenance, so it can't be switched. So you want to remove all actions that manipulate this one power line. Yeah, so this is how we do it. Mm-hmm.
Thanks for the presentation. I just have one question. Is your work going to be applied to which level? I mean, to which level of one of these core operators? So is it going to be applied by the TSO or DSRs? Because you mentioned about this substation.
So the main work we have been doing has been on the TSO level, because there the problems are much more severe, because they have like, so the simplified version is like the one with the congestion, but what they actually have to do, they have this n-1 constraint, they call it, where they have to outage each element and then simulate the power flow, and then they are not allowed to have overflows. Even if one element breaks, it should be still like okay, and they have to satisfy this n-1 constraint by law. And so they actually are really struggling on this side. The DSO level, that's why we had like this FFG project this year. They seem to be like a bit safer in that regard. On the one hand, because of the network structure, they usually have not these meshed networks as we see on the TSO level, but sometimes even have star networks. So they have like one feed-in station and then just like lines going outside, but it's more like a tree in that regard. And on the other hand, so for example, one operator we worked with, they just recently updated the infrastructure, got like huge cables, put them under the ground, and they kind of like their utilization is at 40%, usually always. So that was the point of the FFG project, to kind of look at use cases that might be relevant for the DSO level. And there it seems like they're really, so we could optimize the standard topology, which is like more of an analysis kind of way. And then what they're also really interesting is state estimation, but this is something we haven't worked that much yet on that.
So regarding this topology that you were using for your model, because I think I am 100 is it a real topology that applied throughout the European Union also?
Sorry, can you repeat it?
Is it a real topology that also is considered in the European Union power grid, or I just want some elaboration on
So about so the question is like if like where this network comes from, basically.
Yes.
Okay. So I think this is a research network. So there are different ones. So there's the RTE 14, which is like a small one with 14 substation, and then the IEEE in 118. And these are published by, I think, mainly by the RTE, by the French national grid operator, for research, basically. So even like especially as part of the power grid challenge, they use this with like some abstracted injections so people can work on it, because they are very interested in kind of like finding solutions to this, and that's why they kind of started the challenge in the first place in 2020. This one, yeah.
Can you do transfer learning in general?
Sorry?
I'm wondering if you can use transfer learning. So if you have, for example, that IEEE grid, and then you apply to some real world grid, or do you need to
Yeah.
all over again?
Good question. So the short answer is not yet, because this would necessitate a much more advanced network structure. Like the neural network and how the observations are represented would have to be abstracted from the network itself. So this is where graph neural networks would come in, because then you could theoretically train like a master network and then fine-tune it on the individual grid. But for now, we looked like always retrain it, because our training, thankfully, is actually not that slow. So we train it on our in-house infrastructure that we have in Enlight, and the training times are between like 2 days and 1 week, or maybe 2 weeks, which is reasonable enough considering like the amount, the size of things. But would of course be interested to try out as well. Mm-hmm. All right, I think that's it.
And at this point, I think we come to the end of our keynotes for today. Now we've got lunch in the Mensa again, and we meet after lunch at 1:30, I believe, and we'll keep going with the tutorials.
Okay, you do it.
Yeah, no worries.
Yeah.
Thanks.
So, yeah, that's fine. Okay. Then let's start. Welcome to the next session. We will talk about some basics. You're going to hear a bit about the policy gradients or family of algorithms called policy gradients. In particular, we will look at the PPO algorithm, the proximal policy optimization. Without any further ado, I would immediately start because you already had the introduction, who I am and what I do. So assuming that the pointer works. Yeah. Maybe to first recap, I assume you heard already yesterday by Thomas and Catherine, sort of part of this algorithms, tree of algorithms of reinforcement learning, so where you can split them apart in two branches if you want, so model free RL, to recap it a bit, as well as model-based reinforcement learning. Model-free algorithms basically don't have a model of the world, the dynamics basically, they just optimize directly a policy or a value function. Model-based algorithms try to model the system dynamics, so the environment dynamics if you want so. And there also you can by fork, and obviously this is just a very small subset. I mean, over the years, now we have a platoon of different methods, but one of the most important branches, and you already heard them, most of them, also the talk during today, as well as the last, yesterday, where there's obviously PPO, proximal policy optimization. You heard about maybe some actor-critic methods. You heard also some Q-learning methods in the sense of DQN, probably yesterday also by Catherine. And soft actor-critic was mentioned today, as well as I think when we look on the model-based side, the alpha zero, I think it was also mentioned about mu zero and so on. So that's it basically on that side of the spectrum. To just get a feeling of how can we divide this. There are also methods in between where you say many of them are optimized for discrete action spaces at the beginning. Later on, were adapted for continuous action spaces, such as DDPG, for instance, or TD3, for instance. I'll start directly with the results, because this is kind of reminiscent why PPO is so important in a way, because PPO is actually one of the very de facto standard in reinforcement learning at this point, because it just off the charts when it was introduced works. It just works. So every new problem it can take in some way it kind of works. Obviously, you have to look in details when it doesn't work and adapt and fix it. But the kind of this plot here you see basically the Mujoko environment, where with some several kind of like the Walker 2D, for instance, Hopper and so on. This are just basically some control task where some walking algorithm or something like that with different limbs has to crawl around. And when you look at this gap between different kinds of algorithms and so on, you introduced PPO and so on, and it was basically just taking off from the start. And it's actually really hard to beat PPO. And we will look a bit on how does it actually work behind the scenes, which kind of hacks it has actually, because it was kind of how it emerged to get to this point. And you can follow up then on different kinds of algorithms that build on top. And its importance also of PPO is actually seen in things that you might not see even immediately relevant or related to it. Large language models, you probably all of you know already. but the actually breakthrough was the value alignment of these models, because if you think back in GPT-3, when you had this large pre-trained model, you already saw this few short capabilities of it, but the problem was it didn't produce out of the distribution that you would have expected, like this kind of like answer how a human would answer and so on. So usually when you do reinforcement learning from human feedback, when they introduce this paper, this actually uses PPO at the far right, in the middle, but it obviously requires some other steps beforehand. So what you had here was in the first step, it pre-trained, if you want, to a supervised fine-tuning of a model on large-scale data. In the second step, they had to train a sort of a reward function. We talked about reward functions already and heard about them, how important they are. In this case, they were basically sort of like ranking seems to be easier than having to write yourself all the supervised labels and all the data. So basically, the algorithms were prompted, or the models were prompted, and produced several kinds of options, and people were just asked, which one do you prefer, or which other? So this way, they kind of trained a reward function, as you see here. And with this reward model, if you want, so they basically plugged in now proximal policy optimization and just tried to optimize with this reward model the behavior, the alignment of a large language model, for instance. And this was kind of the breakthrough of ChatGPT, GPT 3.5 Turbo, and so forth. So this is kind of now also de facto standard, this approach of reinforcement learning from human feedback, how we do value alignment in even large language models. And why I like to show this is because, to be frank, I have a very strong opinion sometimes about reinforcement learning. I like it. I come from there and do a lot. But there is actually, to be honest, no real world application out there that really just online runs on the environment. Because you wouldn't risk that, right? That's why we build simulators. That's why we try to confine everything, try to test everything in such a very, very constrained space. Even this is actually offline happening in the background. But this is where you really see an RL algorithm shine in practice, because it has already integrated in a loop and solves a real world problem, which has scaled massively. So this is one of the greatest success stories, in my opinion, about reinforcement learning's application in the real world. Yeah, and maybe also to rehearse a bit, or to introduce a bit, first of all, some notation to talk about, that we are all on the same page about the symbols that I'm going to use. We're talking about the Markov decision process, obviously, with state, action, reward, and some transition dynamics. So state transition probabilities. So we are somewhere at the top here. So with S coming from states, A actions coming from this A for very weird A. Reward functions basically is state cross actions and maps to some real number usually. And then we have this state transition probabilities of the next state given some state action pair. So when we interact with the environment, we saw this loop many times today. I don't have that picture on it. So hopefully this is also counts as a reinforcement learning talk. But basically, this is what you always see in the loop there. And then basically, the reward function takes in usually, this can be shaped and modeled in several kinds of ways, but we will talk about here taking in state and actions, and then basically producing some sort of real value back, if you want so. And we can also talk about stochastic policies versus deterministic policies. Stochastic means just that it's you sampling from an action space instead of having, given some state, the deterministic next action. Yeah, and we also have this so-called terminology of this return, where we have basically from time 0 to infinity. In this case, this is for infinite horizon problems defined here. But that's why also we have this gamma, this discount factor here with gamma k, basically, which bounds such that we don't explode in the values. And we have obviously the action value function, which we will also talk more later, or we heard already also yesterday at DQN, also known as the Q function, which is basically this expectation following policy pi of the return given some state and action assignment to these random variables S and A. And we have the state value function, this V of pi, what you see here, which is the expectation of following the policy pi of the return just given the states. as well as we will talk about the advantage functions, which is important for PPO, which is basically the value function minus, or the state value function minus the value function itself. So this is like a baselining. And we will use this notation for this performance measure, J of theta, which is theta the parameters, and its empirical estimator, J theta hat. So why policy-based versus value-based methods? So let's compare them a bit. What is the advantage of them? Usually we saw the policy-based methods converge faster. We will see why. What does it actually mean to be policy-based? Because policy gradients is a bit of a not so practical name, let's say, because gradients we have everywhere, even in the value, DQN and so on. But in this case, it's about that we train directly with the policy that we are sampling the trajectories from. We're optimizing directly the policy that produces the actions, if you want. So whereas in value-based methods, you had this kind of like, could have had any kind of offline method or any kind of method could have produced samples. And then you try to learn a value function on top of that. How good is any kind of trajectory or any kind of state and action pair? And then you use that basically with an argmax or so to get your next actions when you basically exploit. And there is an advantage to this because now you can kind of learn also the trade-off between exploitation and exploration, which we'll see also later on. Most of these policy-based methods are model-free, but I'm not sure if this, there are so many variants nowadays and combinations, so you can probably combat that a bit. We have also the advantage of this is we're directly maximizing in the direction of the reward function. So our policy maximizes the maximum likelihood in a way. We will see this, what I mean by that in a second, but it's kind of maximizing the expected return or cumulative rewards. Whereas in value-based methods, we have the advantage that they are sort of more sample efficient. We will see in a second why this also plays a role. But you could have several policies, collect them all in a buffer, and then you basically just rehearse the buffer, and you can keep all the samples. We will see that in policy-based methods, policy gradients methods, this is a bit problematic. Many value-based methods are off policy, as I said, because you can have several kind of policy optimizing that. And you compute this expectational values, which I already said. Yeah. So let's try to derive a bit policy gradients. So let's rehearse what the goal of RL is. In a way, the goal of reinforcement learning is to find this kind of policy pi star, such that we have the argmax of the pi, so basically the maximum policy from the values of this expectation, which is following the policy of this G0 given some initial state. If we expand that a bit, we see that this is basically nothing else than just some starting state distribution, P of S, 0, multiplied by, if you want, so this is now the weighting factor of the policy. So basically for all actions of the policy, weighted by its imminent reward. So you have here also the probability of the reward times the reward itself, so because there could be also stochastic reward, plus some overall time steps that are remaining of this transition dynamics. So there's also some probability of transition dynamics that we have here, summing over all, again, policy, pi next actions, given the next state, and next rewards. So basically sort of future expectations, if you want so. And when, so for this talk, I had very sloppy at the first slide a bit with notation, this trajectory like tau. So I talked about R of tau and so on, because tau is sort of a trajectory to make an ease of notation instead of having to write every time S0, A1, A0, S1, A1, and so on. We can talk about like a bit like the entire trajectory. And we say it's basically just a state I, AI from 0 to t. And we can also have this kind of probability over the trajectory, meaning that this is just a starting state distribution. And then you go the product over all policy. So this is like the occupancy, what you see here, basically pi AS. Occupancy means sort of like how this policy distributes on the state actions landscape. weighted by its transition dynamics. And again, the goal is basically to find the best optimal policy here with the expectation over this trajectory, tau, coming from this trajectory distribution if you want. So maximizing this return, so R of this tau here, which is basically our direct objective of performance measure, as we saw earlier, this J over pi of pi, and basically is kind of the main objective of our algorithm. So yeah, we just rehearsed that basically, and now we actually just put in, instead of this pi, we parameterize the system. So we talk about now obviously some sort of neural network, a parameterized system, let's say. So it's the same thing. We're just looking for the theta star, the optimal, if you want, a parameter set that maximizes this return over the trajectory, and therefore we're looking for this equivalent performance measure of J of theta. And how we do this is basically we just do this with gradient ascent steps, not descent, because usually we're maximizing our reward. So in this case, we're trying to compute the next gradient, or the next parameter set, given the current parameter set plus some step size alpha, and then the gradient of this performance measure. So it points in the direction how to ascend. Turns only out that computing this is really hard because of many traits in there, because of correlation, especially because you're highly dependent on the policy that kind of produces these actions. So you're actually learning from the trajectories that you're producing yourself. So when you shift or drift or have a high bias in a direction, then you have to kind of recover from that bias. And if you don't have any fresh samples, you kind of collapse with the policy. And this is exactly where we're going to just spend the rest of the, if you want, hour discussing how can we hack this and fix this in every kind of way. How can we fix the biases? How can we fix the variance that is also implicit with high returns and so on? And how can we actually even do sort of exploration more effectively? And how we're basically just trying to come up with PPO from the initial start. So yeah, basically as this looked in 1998 by Sutton and Bartow, you had this basically as a gradient ascent of this performance measure with some estimator, in this case J theta hat, so mini batch updates and so on, or of some sort of trajectories, subsamples. And then you basically do this gradient with the expectation over this pi parameterized by theta over this entire reward sequence, or this trajectory, cumulative reward. And then you basically have is equal to the expectation of the gradient log pi theta of the trajectory weighted by its reward over the trajectory. And how this came out, you will see basically here, because there's a sort of a trick where this works out. It's actually the log derivative trick that we're applying here. I think proposed by Shakir in 2015, could be also earlier somewhere, I haven't looked it up. But you will see basically that actually the gradient of log p of any kind of function, or any probability function, px parameterized by theta is equals to 1 over px theta of the gradient with respect to theta of px theta, which is equal to the gradient of this px theta over px of theta. So this is basically the trick that we're applying, how we can reformulate what you saw earlier on the previous slide. So when we start off again with this expectation following some probability distribution px parameters by theta of some performance function, whatever that is. Right now we're in general case in this case. If you then do basically this expansion, you will see that you have the gradients with respect to theta of this integral of px theta fx dx, and then you basically do this log derivative trick in here. So you basically just substitute with this position, what you see here at the top, and then you will see that you have actually the integral over the px theta, the log, the nabla, so derivative of parameters by theta, log px theta fx dx, and then you can basically take the expectation out again, and then you see that this is the expectation over the gradients of log px theta fx. So this is how you saw it on the previous slide, if you remember the exact, from the reward to the actual expectation of the log probabilities of the function. So we can expand this also a bit when we work with samples. You can look now, how can this be approximated? So now you have obviously this gradient of this performance measure being equal to these expectations with some actions coming from some policy parameterized by theta, states coming from some state distribution, usually when the starting state distribution, and then obviously the dynamics. And then basically you have this sum over all the trajectory, so the entire return, obviously we're looking always, and we have the gradient of log pi theta of an action given some state. So you have a policy, you give it the state of the system, and then it basically returns you back an action. The question? You mean like intuitively what it means? Yes. Okay, so this is basically the expectation of the log likelihood, actually, of log likelihood given the reward function, because this is a general function, f of x, but you will see that.
I calculate the term in brackets.
Mm-hmm.
That's clear for me, but what does the expectation now do? Is it like a sum over the trajectory? Or?
If we realize it, it would be like a sum over those, yeah. Because it's always over, we're talking about the entire return at this point, over the entire sequence. This is actually, we will come in a second about the reinforced algorithm, and then we will decompose this further. Exactly. So, I mean, you see it here in a way, when you look at samples, basically, what you would do is basically just instead of having, this is exactly what you just saw on the previous slide, just expanded. So it looks a bit nastier, but it's basically the same thing. With the entire trajectory, and then you use samples for that. So you have to obviously, you normalize, and then basically do this sum over all the log likelihoods weighted by the sum over all rewards. And this is exactly what I just said. So basically, that is the maximum log likelihood, that term, which is trying to just weight up and down basically the rewards. And we're working over the entire trajectory here, so not parts of it or so, and we will see down why we're talking later on about advantage functions and so on, where this plays a role. Like I said, R over tau is again over the entire trajectory, and this is the expectation. So it's basically increasing the likelihood of high return trajectories. This is what we want, and decreasing the likelihood of low return trajectories. That's actually the expectation over this R tau, what you see here. And this is actually exactly the first algorithm, the reinforced algorithm. It's an on-policy algorithm introduced by Sutton and Bartow. And you basically start off with some randomly initialized policy with some parameters theta, have some step size if you want so, but then you just repeat until convergence or until you reach your goal. And then you basically just generate an episode. So you really just use the policy, generate an episode. So meaning that you have state 0, action 0, you get then a reward from the environment, and the next state, and so on. So this is what you can think about this when I say sampling or following this policy pi parameterized by theta. And then you have this performance objective in the idealized case, which is approximated obviously sample-based. So you do this over all the samples that you just generated, and then you do this in log likelihood maximization, basically weighting with the reward, and then you just take a small step in that direction. So you just compute the gradients and then take a small step in the direction of the gradient of the higher returns. So you favor in this case good actions, obviously, because you're kind of trying to get more good actions by maximizing and following in the gradient. You also reduce at the same time less performant actions, and this is often called a trial and error approach, because actually what happens now when you repeat the loop, you generate again new fresh samples. And this is actually very important. You always have to throw everything away. So you generate it. When you did the update, you have to throw all of it away. and have to regenerate. So this is just to try something out, you update, you throw away. As you might think of, this is actually, there are several issues with this algorithm. Obviously very computationally intense and wasteful. So that's what I meant earlier when I said the value-based methods are more efficient, because you would store everything in a buffer and then have different estimates, value estimates for it. In this case, you have to throw all of it away and resample. You have high variance. We always talked about the entire return that we're basically optimizing towards. So if there are in the system high values, or you get a lot of like fluctuation because of every state accumulates, or with every transition you accumulate further and further higher rewards. So you will see that the return is basically very volatile. You will see also that this has slow convergence properties. Actually, more often than not, you will diverge. And sampling efficiency, I said already. And usually that's also a problem. You collapse to, so you're actually, especially when you have a random policy, imagine you just get stuck never knowing where to, there's like you need a door or something to open a door, you need a key. So if you never by any chance sample a key and then end up at a door and then opening it, well, you will just collapse with your representation. So basically your algorithm will just randomly run around this room and probably never by chance gather anything meaningful. So this is also a problem. And then there's also like the problem of exploration, that you're not exploring properly enough, because also in this case you're always just maximizing to this cumulative return. But the idea is sometimes you have to take actions that are immediately like harmful, but on the long run basically can help you out. There are many things in life the same way. So in this case the algorithm doesn't reflect that, and it just exploits immediately. And this is a problem. So we will have to also deal with that exploration versus exploitation problem. But first we will start off with some variance reduction tricks. So right now the rest of the talk is going to be just hacks, how to fix this. Or obviously there are some theoretically motivated hacks, but hacks technically. So the first thing is what Levine refers to in his talk as reward to go. There's basically this kind of causality approach where you say that the policy at time t prime, so the follow-up, cannot be actually affected by any kind of reward at time step t, so before it. So you basically say, like, why should you always then care about the entire return? Why not just, instead of, if we expand this again, so we look at the objective again that we just had, and we saw here basically that we go from t0 to the entire trajectory all the time with the entire return. What if we just go from time step t basically to the end of the trajectory? So we basically, when we do the optimization, we don't care about everything that was beforehand, because it has anyways no influence to us. It just creates more and more noise, if you want, or more and more larger values. And just we have this kind of return to go. And this is actually, if you now think about it, what does this actually mean? That's your Q function in a way. That's actually what you actually already heard of the value function, the action value function. So you basically now have this policy that optimizes the Q function. So you're trying to maximize your Q function in a way. Then there's a second trick to reduce variance, baselining, or baselines basically. So the thing is that when you basically optimize, as we saw it earlier, the log likelihood of pi of the entire return, or in the Q function, actually you might have large values, but you could actually just subtract some baseline and then recenter them. So you could have something centered on 0 if you want, or at least smaller values. And then basically you can, the only crux to it, you have to like subtract the baseline that obviously does not change your objective. You don't want to introduce a bias into the system. So in this case, you have to think of what kind of baseline can you subtract here. And obviously a baseline that is independent, if you want. So if your independent is a bit of a strong word, but it basically does not immanently depend on your policy's actions taken. Yes?
How's this different to reward shaping?
Reward shaping, could see it as reward shaping, is in my opinion, is not something you're trying to find a reward that does not bias a system. Yeah, it is reward shaping in my opinion. The question is only what do you, like right now that's what I was thinking, because right now didn't say what you're using as a baseline subtraction. So in this case, you could say this is reward shaping, and you have some algorithm, some B, this is independent of the action selected, and then you basically baseline. If you now basically plug this in just to see if it's really unbiased estimator still, you will see that actually when we do just the entire spiel again of this, the integrals and the log derivative trick, then we see that actually when you take the gradient with respect to this objective, you end up actually with the bias of the gradient of the integral of pi theta tau over the trajectory dt, and this is equals to b of the gradient of 1 as a constant, basically. Now taking the gradient over something that is basically independent of the action selected, and this is 0, so you see that this is an unbiased estimator. But now we're coming to the point where it makes now sense to what do we plug in there as a reshaping, if you want so. Well, if we think about it this way, if we plug in, you saw earlier that it was like the Q function, basically. If you start, this is reward to go. So you had the Q function actually, so the action value function here. And if you now basically plug in smartly something that's independent of the actions, like the value function itself, for instance, so you're baselining, if you want so, with the value function. So for the given a state, what is the entire value of it? And now actually what remains as a delta is the advantage function. So it's basically the advantage of which, if I take this action, I get something positive back. If I take that action, I get actually negative. It's not good. So you're actually recentering around the subtracting the base value function, if you want so, and then you just focus on the actions taken in that particular state. And that just, tells you immediately like which actions are favorable and which are not. Yes?
Sorry, can you go back to the other slide?
Mm-hmm.
I guess was in this step between not the second one where you have then S with the T slash, not the other one. That to that.
This one? Here
yes.
to here?
No, that's clear.
Okay.
The other one.
Here to here?
Yes.
So the idea is it's a causality trick here. So you say that you're not influenced by any subsequent time step given your current time step already you are in.
So Markov assumption?
Yeah, in a way, yes, exactly. Because you say like you have all the information of the system, so you already know where you are, right? Does it change anything on your time steps? No. So it just matters of where we're heading towards, right? So this is kind of the trick, how we get to this point. And then if you think of it, that's why you're evaluating this current time step, because then it's basically you're evaluating the Q function of this current time step.
And they put this trick like saying it's because of the Markov assumption, or they call it the causality?
I think they talk about the causality trick, but it's the Markov assumption, in my opinion. It's the same thing. Correct me if I'm wrong, if someone, but yeah.
Maybe, yeah, it's the trajectory, they revert from there on only counts.
Mm-hmm.
And this is the causality, which is me. The rest would just induce some noise.
Yes, but in the way it is a Markov property, because it happened already.
You can do it.
Yeah. Exactly, so, yes?
I have one more question about on the next slide, the advantage function.
Where is, wait, here.
Since the value and our state depends on our policy somewhat.
Yeah, that's why I said kind of, but not in this optimization step. I know it is always, if you think about the entire trajectory, your trajectory only obtained obviously by some policy that you got there. And obviously in this kind of particular state you obtained only because of some sort of policy. I know, but it's more that decoupling it directly from the current optimization. So when you would take an action immediately, and this would now kind of change, obviously, based on would change your gradients based on whatever you put in there because it's dependent on the action, then you have a direct correlation there, and then you would basically change the objective in some certain way. So you're just adding in the way just a baseline that is in a way independent, but not obviously fully independent. Yeah, please.
My question relies more on the philosophical side than mathematical. So
okay.
Pi variance and
low bias in traditional machine learning reminds me of overfitting.
Mm-hmm.
Does it mean that some policies could overfit, as in you play too well, you learn to play too well in an environment, or is it such a thing as?
That happens all the time. That's why we need exactly some tricks to, because technically this is actually in RL. This is one of the crux of RL. It's so hard because of this correlation where your policy is direct influence on your freshness of samples and goodness of samples. So you're technically the worst if your policy is so bad in the beginning and it just gives you, let's say, always the same action or always the same steps. You're kind of trapped because you will only optimize from that. So you will never see something else. So you're just fitting exactly that noise all the time.
But also here you have a lot of variance, which means you need a lot of samples to get a meaningful estimate for this.
Yes.
So this is the variance problem here. And then it goes into the optimization area step as well.
Yeah. And on the next slide, you will see anyways exactly this variance bias trade-off. So you see basically you can decompose actually the variance of some expectation of the x squared, so some variable, this is now generalized again, minus the expectation of x squared. So this is this decomposition that you can form. Now if you plug in, if you plug in the variance over our log likelihood of this return minus this baseline, you can see that if you expand this, just becomes more messy by a lot of variables, but basically it's the same thing again over the entire trajectory. You're doing the log likelihood of this baseline subtracted return squared minus these basically baselines are, as you see here, unbiased of this expectation of this log likelihood of, again, this subtraction here to the square. And then you see that you can just cancel this out, the bias. You just can remove the bias. And then if it's independent of your actions. That's an important part. Yeah. And one thing that we just skipped for now, because we never mentioned it, we just said this is kind of the Q function there, if you remember now back, with the return to go. But actually what we introduced, if we introduce the Q function actually has a dedicated functionality now. It kind of acts like a critic in a way. This is where the name actor critic comes from. Because the actor, if you now decompose this, if you think about it, you have the actor, which is the policy, which creates actions, right? Given a state, you create an action. So you act in the environment. Whereas the other part of it, the critic or the Q function, if you want so, or advantage function, we can talk, because that's why I listed all of them. Now here, the steps to recap. If you look at the reinforce, you just had the return there. So you basically had always the entire return, which was obviously very messy and noisy and so on. But then we had this reward to go. We actually saw that this is the Q function itself, right? So in this case, we already had a sort of the critic for some state action pair. You kind of analyze what is the value of it. But if you then do this baselining, what we just saw before, you actually end up with this, what was at the beginning also in the notation form, the advantage actor critic or advantage function, basically, weighted actor. So meaning that in this case, you have the log likelihood of which more advantageous action you should take in this given state, or with the state action pair, if you want so. So this is actually really cool, and this is a very, very already very good smoothed out and variance reduced version of it. You can do even like TD actor critic, sort of like temporal difference errors between actions and so on, but I won't go into any details into that, but technically you can even do here some further abstraction of it. And you can also read the papers that I basically listed below. But now this is exactly what I just tried to summarize very nicely. The critic itself, given a state action pair, evaluates how good would this, the sample behave. And the value function itself is just reducing the number or centering the numbers if you want. So the actor itself obviously tries to maximize again the best action if you want now. And if you look at, let's just say this decomposition here of this Q function is basically just the expectation over the immediate reward plus some discounted future expectation if you want, so of value expectation. And the advantage is actually when you plug both in, the Q minus the V baselining, then you see that this is actually the immediate reward plus discounted, and this is actually very cool now, discounted differences between two value steps. So this basically the ST plus 1, so the next state, and the current state. So it's actually now it's very cool because now you have just one estimator that you, instead of having two functions or so that you can have to carry around, you can actually show that you have just now a value function which you just put into the delta states if you want, so one discounted one and one from the current time step, and then basically the immediate reward. And this is how you estimate your advantage function.
But I have just one question there for the Q value, how you put it. This value function for the next state is dependent on the action you take, and I don't see it there in this E. Or I'm missing something.
So you mean here?
Yes. So
yeah, this comes from the policy, basically. So you see, this is how you saw probably also yesterday how you can decompose basically the Q function, state, the action value function. And maybe what is missing here is the expectation over the pi, but the idea is that you have an immediate reward plus a discounted next state. So the action basically just is within the reward if you want. So remember that the reward actually depends on state and actions. This is how you get your reward. So basically, this is where it is embedded. It's missing the pi maybe here to make it very clear that the expectation comes from that. But yeah. So basically, at the end of the day, you just are with the immediate reward plus these discounted next step value, if you want to, function outcome, and then minus this current time step value. And now this is really cool because this is easy to optimize. And now you have a policy which you optimize and a value function that you have to optimize. Another problem is, if you remember now, if we go back to the beginning again, I said that PPO is reinforced is very wasteful. You have to like generate tons of new samples all the time and then just throw them away. And it would be something cool if we could have something like a buffer in the case of DQN or something like that, or where you say like our Q of policy methods, where you could just have a buffer where you can sample from, and you have you can reuse your samples multiple times, because usually your gradients are anyways very noisy, and you can always subsample from your buffer. So it would be cool if I can maybe 3, 4, 5 steps down the line still use some samples that are close enough to my current policy. But that doesn't work, because otherwise you would optimize the wrong objective. You would optimize something from your old policy or from a different policy, which you would mess up your gradients. And in math, basically, there is a trick how to do this. If you have two distributions that are kind of not aligned, what you can do is basically you can do importance sampling technique, where you have this like a density ratio, basically what you correct for. And then you just transport from one distribution to the other, which would be in this case your old policy values or distribution versus your current policy value. So to be more concrete, you have this expectation over some value x coming from some distribution of some function x, whatever, in general case again. And then you have basically this integral over px, fx, dx. And if you now want to correct for the distribution, you just basically have, let's say, a second distribution q of x over q of x. You can just introduce that basically. And then you basically can see that you just have this target versus source distribution as a correction. And then you just have basically importance weighted or importance sampling weighted estimator. And you basically now just transport from one distribution Q to P, for instance. And if you plug this in again, in our policy gradient method, we have basically this kind of, obviously in this case, pi theta and mu, in this case some other, your old distribution if you want, so becomes like a sort of a ratio, like a reweighting ratio of your return trajectory. You can expand this again, look at the full beauty of the product if you want so. So we have your starting state distribution of P of S0, and which is basically the products over all policy pi times some transition dynamics, obviously, reweighted by starting state distribution again with some other policy, some outdated version of it, if you want, so with the dynamics. And this ratio becomes now important because we can recap again, but I mean, we made it very clear that the problem is in on policy methods, you can only optimize on your current target, what you're generating, and you are outdated to your old samples, and now basically you want to correct for that, which I denoted here in the solution, important sampling solution version of it, of the algorithm, where you have now these actions coming from some old policy. So you see AT coming from some pi theta old, if you want so, some your previous buffer, if you want so, of samples that you collected. The state obviously is the same as before, and then you have this, sum over all the log probabilities with the importance weighted samples now for the correction. So you have now this correction for the distribution, and then weighted by the reward, which we will see again is going to be the advantage function and so on as we had all the time. But now, obviously, you have some assumptions. This has to have the same support and so on, because otherwise this would blow up. And because actually that's the most important thing here right now. If these two distributions are too far off from each other, so you can't do this for infinity. So you can't do this like, forever. You have to at some point throw out your samples. Because if your distribution shifts a lot and then becomes like really, really outdated, and you have something with very small values divided, this will explode. So in this case, you have to have some method that kind of constrains your policy, that you remain as close as possible to your previous policy, but still can move in the right direction all the time. And that thing is actually called you need sort of a trust region or trust region methods that have been developed, TRPO. And we'll see it in the tutorial by Simon also. We'll introduce this. And you basically will see that this is an algorithm that you have this kind of, you're at this point, WK I think or so from the schematics. Your objective is to get here in your fitness landscape. So these are the contour plots, if you want, of the landscape. And if you would just do really simple, just line search the optimization in the direction of where the line search would push you in or show in direction, you would just overshoot and go in some way, just down the line with the gradients and with the optimization. Similar, if we would just take the gradient step, the gradient direction shows just downwards here. You might also overshoot and basically show, because you do mini-batch sampling, don't forget that, you will have some messy and noisy gradients pointing around. So, and if you take a wrong step or so, or too far the step, then you can end up in a region that you just blow off basically with your policy. And then basically, if you do this kind of trust region optimization, this is what you see here, kind of this circle. You kind of take sort of a compromise step, if you want, so within the direction of gradients, but also in the direction of the line search. So you basically have this trust region step, what you have. So this is kind of the schematics of it. The math behind it is it's a constraint optimization problem that you're solving, or what they're solving. It's basically, again, this expectation over this ratio. It's not simplified, so you basically focus only on this. So you minimize basically this theta over this ratio with weighted by the advantage function, so as we saw earlier. And then you basically have subject to this expectation over the Kullback-Leibler divergence. So the divergence between these two distributions, where one is the old distribution versus the other one is the current set of parameters on your distribution from the model. And this has to be below some epsilon. Now you could do this quadratic optimization problem and so on, which is, nice, and is interesting to look at. But in practice, what actually they came up with as just an equivalent representation is you could just do a penalization basically on this. So you can just reformulate, and you can look at the paper how they do this, but you can just reformulate this constraint optimization problem as a basically penalization weighted by some beta. Beta is just, if you want to, a hyperparameter. And then you have this kind of Kullback-Leibler divergence subtracted from this ratio. So this way you kind of constrain your policy to not move too much away from whatever you had right now as parameters, such that you avoid that you explode because you don't have sim support or so.
So the divergence is kind of to measure the difference between
Yes, exactly. We just want to keep the probabilities as close. The further away the policies would move with that update step or so, the more constrained you're penalizing more, and you're kind of keeping the parameters close to the previous policy.
I have a question because it's just appears like it looks pretty much like augmented Lagrangian then, right? But in that case, you would also have to optimize for the Lagrange multiplier.
Yes, with the Lagrange multipliers, yes.
But apparently we don't do this here, right? So the question is how should the algorithm beater, which is basically fitting in this concept of having this augmented Lagrangian approach.
How you choose it? So the question is how you choose.
How to choose beater? Because otherwise, if I just take the optimization problem.
You want an honest answer or the hyperparameter search? Maybe there is a way. I don't have it off the top of my head. We can look at it if you want at the paper, but hyperparameter search. That's the machine learning approach. Yeah. So, I mean, if you want, I can take a longer answer to that. In my thesis, I have basically talked about parameter choice issues in domain adaptation. In this way, if you want, so this is a weighted, basically source domain, target domain, if you want to go to this analogy, basically. And now we have developed methods that you could basically apply now for, where you still have to train a sequence of models. But then you can use either model selection methods, how to select which one is best, based on some trained validation and test split, where test is just used at the end and validation is used to tweak this hyperparameter. Or you use an aggregation method, what we developed, which you combine all models if you want so. Then you don't have to choose the beta. So this would be the long answer and some shameless self-promotion. But anyhow. But it's still tricky for RL. Our method was developed for supervised learning and unsupervised domain adaptation. Not sure if maybe it's a good experimental paper to look at for RL. Now, the last step is actually now to talk about trust region methods. Although this is a bit, I'll say a few words to trust region method in PPO. But if you now look at the PPO paper, because this was kind of the last step, if you want to, from the TRPO to PPO, they kind of figured out that you could do this kind of trust region optimization instead of doing this, divergence and so on, and the constraint optimization, etc. You can actually just do some sort of clipping. So you basically can just say you have this expectation of the minimum. There's like two parts. I'll show you a visualization because this also trips me over every time looking at it. But it's basically you have this phi in this case here, which is the ratio to make it short, to not blow it up, weighted by the advantage function. And you take the minimum between that or the clipped version of it. So basically you're trying to say like you're just having this phi clipped between 1 minus epsilon and 1 plus epsilon and then the weighting of it. What this does, I mean, they claimed back then that this is a trust region method. Turned out later it's not. It's more like you encourage or discourage basically large updates, but it's not really a constraint optimization problem as you saw it earlier. You cannot guarantee that in every step basically you have a more optimal policy afterwards. You can still diverge and explode and so on. I mean, in practice versus theory, there's always, anyways, also with TRPO hard to optimize, but it's not fully a trust region method if you want to take the short answer to that. Yeah, so in this case, maybe let's just look at some table and some visualization how to interpret this weird clipping. So if you have some probability of parameter set, in this case, so your policy if you want so, being larger than 0, or the probability being larger than 0, then basically you have some, like you can look at this 1 to 6 steps basically, and we look at the different cases, what that means. So you have here the advantage function here. You have some random value for the weighting, which will be applied, and then you basically have the objective, if it's clipped or not, because now it depends if in which case you are, and the sign of the objective, and you will see also at the end if you have gradients or not flowing. So let's go step by step, at least for one or two cases. So if you have here basically some probability sampled within this interval from 1 minus epsilon and 1 plus epsilon, let's say your advantage is positive, because the advantage is now it tells you good action, bad action, depending on what you selected. Then you basically get some sort of no clipping, first of all. Obviously, the sign is positive, and you get gradient flow backwards. So you can do the optimization step. Same goes with the negative part, just the sign flips. But if we look at, for instance, if our probability or values are basically smaller than 1 minus epsilon, for instance, means that we have this 1 minus epsilon times this advantage function. But now what we see here that we're clipping off, and we're cutting basically off the value, and then we're prohibiting gradient updates in this direction. And this goes the same for the positive version and so on, or larger values than 1 plus epsilon. And you see it here in the graphics below. Here is basically where it would be with 1, as I said earlier, or here is with 4, where you basically get cut off. That's why you see this kind of flattening curve. This is how you can kind of get an intuition for it. Yeah, and to recall one more thing, because there's still one problem that we haven't tackled yet. This is like an intermezzo to maximum entropy. The issue, what I also said at the beginning, is diversity of samples. So we talked about mode collapse of the policy to sort of very poor samples. And it's about exploration versus exploitation, because right now we're just exploiting still. Whatever we have here, we're still just exploiting that. But sometimes, as I said, it is advantageous to not just take always the best action or the best performing value that you have right now, but it would be advantageous to just also randomly sample sometimes some poor actions and so on. So have some probability where you just try around, and then maybe you end up with a better solution at the end of the day. So that is kind of the idea behind it. And for that, we can basically just add a very, very simple trick. We'll just have the same objective as before. But now we add, so imagine this would be now the, this is the simple version of it, but you imagine he would be PPO instead of the log likelihood of this policy and the advantage. But you now add just basically this beta weighted, there's another hyperparameter again. It's not the same beta as in the constraint problem. There are two different settings right now, what we're looking at. So it's some hyperparameter of the gradient of the entropy, basically, of this policy. So what you're doing here is actually, when you add it, you're kind of now pushing for higher entropy. So you're pushing the probabilities of the policy to produce more randomness. This is obviously now very harmful. So if your value beta is too high, you just do random things all the time. So this is the most finicky, or one of the most finicky parameters that you will also encounter when you try to really hands-on do something. When you play around with this entropy term, too high values, nothing converges, nothing learns. To low values, you will immediately see that you might just get stuck in a local minima. And now you're basically trading off, because one tries to exploit, so you try to exploit always the best action possible. Plus, on the other side, you try to explore as much as possible with the policy. So you get the most diverse policy, if you want. So it's a win, I would say. Yeah. And this actually concludes then. We're coming to the, if you want, so final objective. We're actually at, proximal policy optimization algorithm itself. We have basically here now, we're initializing a policy pi, parameterized by some parameters theta. We are looking also, initializing also some critic. In this case, if you remember, we said that we have some value function, basically, in this case with this new omega, parameterized by omega, both with random weights. And we create sort of an empty buffer. We saw that we can now have some outdated samples if you want, so we can collect them. Over time, we just have to reset the buffer. Then we define sort of some step sizes, and then we actually repeat basically for the entire trajectory. We generate and store new samples, and we have we generate actually this kind of tuple, if you want so. So we are basically having the buffer. We're unifying the buffer basically with the new trajectory, which is state, actions, reward, sequences. So basically we have this next state, and we have this entire trajectory stored in there, multiple trajectories obviously, and then we can perform actually k update steps. So this is the idea now. Instead of just updating once and then throw everything away, now we can at least sample multiple times or so if you want so, and then update multiple times so that we can. Because usually in one step with the step size, you don't end up with learning the entire trajectory. And then you can do up to k steps. This was another hyperparameter that will trip you over probably, because if you optimize too many times, usually this is roughly 3-4 updates or something like that, or I don't know, somewhere in that ballpark. Because if you update too many times, then you're just memorizing again what you're doing there, and then you again have other problems. And then you basically sample a mini batch from that buffer. This is basically what you see here. You also have to store the log probabilities. This is what I have forgot to mention. You see here just the old policy probabilities, but technically in practice you store also the log probabilities because you need them to compute below then the importance ratio. And then you basically also compute the target function, so the value target basically, which is this reward, this random variable, what you see here, plus some discounted value in the next state. Then you compute the advantage function, which is exactly this value that you just saw here, minus the baseline of the current state value. So this is the discounted value of the next state, and this is the current value. So this is exactly the advantage function you saw earlier. Then you compute this importance sampling ratio. This was this phi hat. You obviously have an estimate. And what you do actually in practice, because these values are obviously very, very small, so there's a 0 point whatever, depending on action zone, but you can have very small values. So for numerical stability, you usually optimize with the log probabilities of that. So you have now the log probability or the log ratio, basically. And then you basically have your objective for actually have two objectives now that you're optimizing individually, but you jointly optimize them, obviously. So you have the clip objective coming from this, like with the parameter theta and omega both together. You basically have this negative expectation over the negative in this case because you're actually doing it in practice. You're computing a loss, so you're still minimizing, but you're actually maximizing the return or the objective that we had at the beginning. So you have this expectation now over the minimum of this exactly clip error. So you have this importance ratio weighting the advantage function parameterized by omega, and then you have this kind of clipped version where you have this importance ratio with the 1 minus epsilon and 1 plus epsilon region that you're looking at weighting the omega at the action, advantage function. Oh. And then you have obviously the second optimization that you still have to do, because right now you would just optimize the policy. So this is your actor. This is the objective for the actor again. But you have to jointly optimize also your critic, because you also have to update your estimator for what values you have, all the state values. So you basically do, in this case, this new target minus this kind of like current state and square it, basically. So you're trying to get a better estimator for your targets. And then basically you just have the last term, which is the entropy, just added to have the highest diversity, the most diverse policy. And if you put all of these objectives together in one loss objective, if you want so, then you have, again, the value, the clipped policy update, and the entropy. And then you compute the gradients with respect to this loss, which is basically the next step. In this case, again, minus, because we're reducing a loss, but we're actually maximizing at the same the policy. That's why we flipped here the sign. And then we have basically a update step of the theta, and you have an update state of the omega as well, obviously, because both happen with just different step sizes. You could, or it could be the same step size, but anyhow. So the most important thing, or very important thing here, is obviously that your kind of value function is kind of ahead of your actor, because it kind of should be a bit giving good estimates, because if it's always lagging behind or really poorly, then you will obviously have a really hard time for your actor to really find the right direction to move and to sample. So sometimes people do also like different kinds of, you update more often the value function, for instance, versus the policy and so on, or you have to be very careful how often you do this k steps and how many times you update the policy. All these things matter. And it's very finicky. So obviously PPO is no one-shot solve-it-all algorithm. But I think the cool part of it, this algorithm, is that it has very meaningful defaults. So if you look at stable baselines or something like that, or if you look at Ray, for instance, I think, or what is it called? Thank you, exactly. Then you basically have usually very out of the box. You just call the algorithm, put in usually an environment, and that works. If it doesn't work, then that's the moment you anyways have to explore a lot. So, and what I always like to also give us like sort of hints and directions is, as well as in life, also you should always stay in shape also with your tensors and your basically your functions. This is something that happens so often when you implement yourself PPR. If you do that, I don't know, but that sometimes you just see this, quickly expansion of vectors and tensors and all these ratios and all that stuff, and then things just blow off. It still work, but you never see an optimization. So these are things that lessons learned what cost me weeks sometimes in the background. Normalization of the reward function is still important. Because if you still have high values and so on, even if with this advantage baselining and so on, there are other tricks in the appendix and so on of generalized advantage estimates that you can also look into, which is a bit more advanced ways how you can have this kind of weighted, if you want, so estimates of the reward. But we can look at that if you want. But I think it's still in a way. With the algorithm itself already advanced enough. That was also my question yesterday to Razvan a bit. My experience is that these algorithms quickly divergence on when you add a transformer or other things like that, this is really hard to control for. We heard it yesterday also because of the softmax properties of it and so on, and that it kind of has this uniform distribution when you sample them from and so on. So this is really hard to control for. I usually found out that shallow networks, simple networks, MLP, so some things like that, even if you go with recurrent connections and so on, is going to be very hard. So you will see that. Try, if possible, every time you use this kind of if you, let's say, change the architecture of the algorithm, try to keep it simple first, MLP layers and so on. If you see that doesn't work, or if you have some properties that are non-Markovian, observation spaces, etc., then you have to anyways go more complex with statefulness and so on of the policy. We talked about hyperparameters and we have to play around. So there is a lot of RL is just trial and error most of the time. So you just have your environment set out, you have your policy, the algorithm, that whatever you choose, with your policy, with whatever architecture you choose, but then you see that it doesn't work. That's usually the first run doesn't work. Second run doesn't work. A week later, doesn't work. But then afterwards, it's like, okay, maybe it was just this or that hyperparameter that kind of screwed you over. And always change one thing at a time. Change small things. When you change the entropy, stick with that and see if that works. Try to log all the stuff. Try to visualize it. We have also things where we look at the gradients and so on. Do we have update signals? If we look at the cumulative reward, does it grow or not? And so on. Try to visualize things. And like I said earlier, important is also that the critic learns ahead of the actor, because obviously if you have a really bad critic, your actor will just behave as poorly as your critic, obviously. So in a nutshell, keep it simple, play around with hyperparameters, enjoy your life, use more advanced techniques, and there's some troubleshooting, things that you also can look, but I actually mentioned this, all of it. Some short merchandise if you want so. You can also join our, in the past it was called RL is all you need Discord channel or server. It now became more general because AI is all you need, obviously. If you want, you can be part of some 400 plus people from RL, from machine learning, some of them students, some of them from the company's side, some very advanced, I would say. Some shameless self-promotion. Again, what do we do with RL at Extensity AI? We use it basically, you saw this reinforcement learning from human feedback that I told you at the beginning. So you were trained basically through humans. They kind of label, this. So they basically have this ranking. So you sample different trajectories based off some prompt. You let it complete, and then you have the humans label and say I like this over that prompt and so on. The question is only, does that scale? And for us, we said that doesn't really scale, and we've introduced a paper that does multiple things. There are some parallels also to reinforcement learning, but I don't want to dive too deep. But one of the things that I introduced in that paper, in the symbolic AI framework paper, which you maybe should take a look at, is the vertex score. Because the vertex score is basically a way how to do a multi-step trajectory quality measure of a trajectory. So a multi-step generative process, which can be used as a replacement for reinforcement learning from human feedback. The idea was to use sort of like this embedding distribution that you're aligning between two distributions. Now you need a reference distribution and you need a target distribution. The reference can be obtained oftentimes through some oracle. Try to clone GPT-4, for instance, its behavior. This could be a good oracle, or some intermediate steps how you can come up with the distributions. But if you're interested, you can look at that. We do also some RL at the company. Yeah, I would say, well, but ahead of the time, so we have some time for questions, and then we would go over to the break. Please.
I like your analogy, like life, reinforcement learning. So in life, I have gave up many times in some activities because I thought the effort wasn't worth it. The juice, they say, isn't worth the squeeze in English. Sometimes I never knew how close I was. I didn't give up, like German, and it paid off, but it was really frustrating. So how do you know that you should start over with a different initialization? Because we know from Rezvan from yesterday that it heavily relies on initialization. How would you decide to give up?
How do you decide to give up? Yeah, so the question is, how do you decide to give up when you see that nothing works during the optimization? It depends. In my opinion, it depends on multiple factors. It depends on how willing are you to really make that work, or what's the stake of making that one particular algorithm work. I usually try to, let me address it a bit differently. For me, RL is not the first choice, usually. So this is like, RL is the second to last option. The last option is meta learning, and that is anyways all hell breaks loose. For me, it's like try simple things first. When you see that cannot be represented for your algorithm doesn't work and so on, then you usually end up in reinforcement learning. Now you try in reinforcement learning. I think reinforcement learning is still in its early phases. Can debate about that. Some might say no. We have seen StarCraft and whatever, but also keep in mind what compute they had and threw at it. So if you have 10,000 nodes and you can just parallelize huge deep neural networks and 10,000 instances in parallel for 3 months, yeah, it depends on your resources, what you have, right? So it depends on what's your objective, what do you want to solve, do you have to solve it, and then like resources, what you can expand at. And you should anyways try always different algorithms. But instead of just stupidly trying every algorithm, think about, first of all, do you capture all the traits or all the important aspects of your problem? Because sometimes it's just, for maybe one thing you're missing because there's a hidden confounding factor in your optimization and you don't see that, right? So it's actually not a Markovian property then what you're actually optimizing, it's like a partial observable setting, right? So you have like this kind of, You're not even looking at the entire state space, right? So you just have an observation. That usually happens. And so what do you do then? You then have to see that somehow happening, and then you have to have maybe some traces of like state actions and so on. So you suddenly have a stateful policy that is not just Markov property, but it kind of needs memory from the past, what happened. So then you end up in LSTMs, other things that you have to integrate into your problem. So that's probably the first thing I would try before even trying any algorithm. Really understand if the problem can be solved this way with the Markov property, whatever setting you have. And then you have, in my opinion, to try several algorithms with several hyperparameters, and then you have to scale that a bit. So that's always, RL is always like a problem of more orchestration of the code and running it on with hyperparameter tuners than it is, yeah. Does this answer your question? How? No, for me it was like when I wanted to finish my PhD, there was no hurdle. I had to finish it somehow. So, well, throw all compute I had at it, right? So don't give up, but never back down. I mean, the problem is like, the answer is you don't know the unknown, right? That's kind of like the problem of it. You don't know, is it the wrong problem? Is it the wrong algorithm? Is it just the wrong parameters? You don't know your...
But as I said yesterday, if it doesn't work out right, then maybe you should go a step back and
exactly.
Do the basic debugging stuff, because we're very, we really try to optimize parameters very early, although we have the faulty code still running, right? That's the point. And you will, if you do this here, you will just suffer. That's
exactly.
That's the conclusion.
That's what I said with the stay in shape and so on, and the analogy to that. That was the fun part of it, because at the end of the day, it was many things were just stupid bugs. I thought the algorithm works, everything worked, it looked all sensical, and then you look at it and see like, why does this vector extend to a matrix, and what the hell is happening here? And it just happened at some point after 2 weeks debugging. And you're like really frustrated, and they're like, okay, now we go back and then just update that, and suddenly every hyperparameter works because it was so easy.
Yeah, just a very quick yes/no question. So for image classification, for example, I'm plotting the loss on training and validation set. There is a definite point when my validation loss exceeds my training loss. Definitely, I know from this point there is no benefit in training because it's going to be overfitting. Is there such a definite aha moment in RL? Oh, thank you.
No. Whereas you will always see that's the most shakiest thing that you always see in reinforcement learning. Like you usually see the loss curves go so nicely down in any kind of like supervised, unsupervised setting and so on. You see the convergence property, you see then maybe the generalization property when validation goes up and so on. In RL, you see nothing, you see then it goes up and suddenly it breaks down. And then this fluctuation of the loss curve or of the reward function, if you want, is like so unpredictable. I haven't identified it, but that's actually what you try always to smooth it out. So you try always to get a smooth objective and so on. But I don't know. Anyone a better answer than that?
No, back to the give up topic before.
Why does everyone want to give up? Was it so horrible?
No, I've seen in many implementations you use the hyperparameter episodes, so you train a fixed amount of times. Or iterations. So why not use? So in real life, I'm not going to train it 100 times and then I stop it and okay, I'm done. Normally, if I'm not getting better, I stop. So why not using such things like simulated annealing from operating research to decide when it's time to stop?
The learning, you mean? I mean, you use anyways, you have checkpoints and all that stuff, so you always see when the policy then breaks again, because it's sometimes optimizing the policy too long, you see that it almost converges and then it breaks again. Right?
It breaks conditions to, okay, now I stop.
Yeah, but there's one interesting point, because maybe in Pong, right, this Atari game, and when they introduced the first version, it is on Pong, at first it just rubbish, then it managed to play properly, it was compatible to the human performance. And then suddenly the agent figured out a completely new way by just blowing a tunnel on one side of the screen, and then the ball would just bounce in the back and would just remove everything. And that you would just break the what you trained
Yeah.
before if you just break it outside.
That-
That's the reason.
That's exactly the learning of it, because the problem here is like, usually your objectives are not so easy, right, that you could just directly optimize, because otherwise you would use anyways a supervised learning algorithm or something very simple, right? Usually with the reinforcement learning, you actually try to sample actions and try to interact with the environment in some very non-smooth and very usually undifferentiable way, actually, because that's why you have a reward functions in a way, right? Which, because otherwise you would just do supervised optimization and so on, right? So the problem is you will see then convergence, you will see that the reward and cumulative reward grows and grows, and then it breaks. Why? Because now it tries a different path, maybe it's just. That doesn't mean that the algorithm just broke also, but at this point now it just sampled, ended up in a, like I said, more unfavorable path. But at the end, it turns out that shoots then up again, and then basically you just converge exactly to optimal solution. So if stopping earlier means missing the optimal solution. So yeah. So yeah, this is but there are ways. I mean, generalized advantage estimates basically we have ways to like traces that you can. There are ways to try to, because that's what you usually try to smoothen out your reward and all that stuff, because that's the problem, right? The more nonlinear and the complex and noisy and whatever, and there are ways. I haven't talked about this, but you can look at it if you're interested in, where you have this kind of like sort of eligibility traces of the reward or discounted weighted k-step rewards and so on. Whatever. You can look at that. There are other methods that can give you more and more tricks if you wanted to fix it. Because at the end of the day, if you look at Rainbow or any kind of this kind of algorithms, it's just also a collection of all the hacks to get Q-learning to work, right? In a way, you can see this the same way, that at least how I see it.
For addressing a problem with reinforcement learning, how do you decide if it's the right tool to use?
If it's the right tool, or what?
Right tool, the right technique to use.
Like I said, mine is the second to last. I go all the methods before. I try to closed form solution. I go to a function approximation. I go to whatever, and then I end up in RL. And then, well, I have no idea. Let's meta RL it or whatever. Meta learn it is the problem, and maybe some of the sub anneals or whatever work at some point. So that's kind of my approach. I wouldn't go first RL if it's not necessary. I hope I'm not disagreeing with the RL community now.
I'm not sure if we're still in business.
Yeah, please.
Since you come from a computer science background, I have a feeling that there is no if we want to talk about complexity, because with traditional algorithms there is always this complexity, like time complexity of an algorithm. It's O3 over like O of n, whatever. And it seems like these things don't fit in that paradigm. There is no notion of complexity for RL. It's not even NP hard. It's something totally, absolutely different.
Well, it is NP hard, but yeah, I mean, the problem you see. I mean, technically, it's not even like IID, right? I mean, we're doing it in a fashion with these buffers and so on that we do IID sampling and to learn from it with the algorithms that we know. The crux of it, actually, if you think even about online learning, because like now we're always having usually we assume that we can create the entire trajectory, right? What do you do when I tell you the entire trajectory to generate costs way too much, and you have to like have only sequences of it and so on, like in a continual fashion, right? As Rizwan and so on talks about. And then this entire assumption of IID is actually broken. Now you have to find hacks and tricks around that we can apply our same tools. It's a broad question. There is no complexity measure of RL policy to see how many bits do you need to fit whatever kind of problem. Because there is none for deep learning in a way, right? You don't know what's your complexity that you have to have your deep network that you can solve this kind of problem. It just turned out that was actually this double descent curve, if you think about it. There's no notion where it says like from this line onwards it's going to descend again, right? So you have here your value, your validation set, basically your validation error goes up, and then there is the point where it goes down again, just by over parameterizing it to the extreme. But where is the point? Like, what is the value of that point, right? So there is no complexity measure for that. So I don't know. And for RL, it's just even harder. Or deep RL, when you combine both, let's say this way.
Maybe the closest thing would be the sample
but it also depends highly on your learning algorithm, isn't it? Because like the sample complexity in a way, or the complexity of, you see sometimes in the 10 million steps and things, how they optimize and so on, but then you just switch the algorithm and suddenly you see algorithms and they can work with, magnitudes less. Maybe, yeah, maybe that's a way to measure it. But if someone has a theory, please work on it. That would be cool.
But wouldn't you need convergence guarantees to have complexity bounds? And we don't have that, right?
That's my problem. I don't know how I would approach this.
May I even ask, how do we categorize the problem themselves? So is it harder to teach a drone to fly using RL or teaching a Boston Dynamics dog to run? So how do we, because the whole paradigm about NP complete, NP hard, strong, is there is categories of hardness for problems. They keep getting hard. Is there any way we could compare tasks, RL tasks, on which one is harder? Like states, I assume Go is harder.
I don't come from complexity theory. I have no idea.
This would be extremely relevant when trying to use it in the real world. Because it's always, you have to estimate how much effort do I need if this company wants to use it. I mean, Kai said they have 10 million, they got the budget for the project, and someone's at the top of the project saying, I want it 10 million, this is what I can offer, this is the use case we have. How hard is that going to be? And as far as I know, in like real world RL, there's no one who even touches that. Even tries to use it. I think that's really useful, especially for probably even more so for practical uses of RL than in the theoretical case. But I don't know. So I'm not aware of anyone who's thinking about it or trying to. But I think it would be very important, and not just for like the fun of figuring it out, but for being able to say like this problem, this is how we want to use it, this is what we need, these are the resources we need to do it, and there's a chance that it.
Well, my point is a bit like if you can answer that question, you're kind of tackling the P versus NP problem, right? I mean, because if you can then tell this you have to do to get this kind of algorithm in polynomial time done and so on, then then you know it.
The thing is, and that's the point, there's no convergence. Also, you're using RL for problems you don't know the solution to, otherwise you would do something smarter. This is like all of these machine learning tactics, I have no ideas, I'm just throwing it at statistics and hoping that it solves it for me. So you're kind of asking the question in reverse, if you could answer that, you wouldn't be using it in the first place.
Yeah.
But I still think it's
The question is valid, but there's no, I can't tell you the answer because I have no idea. And if you work on this and you figure it out, I think this is going to be at a huge value to everyone.
That's in real world though, it's that the algorithm approach is too slow. For example, the control bandwidth is too low algorithm. But if you train with a relay,
sorry, acoustically I can't, what?
If you use an algorithmic approach, for example, I don't know, find the inverse of the models, use that to whatever. It could be too slow. But if you train it with agents, you can have high.
Yeah, I mean, RL is used in a very diverse setting anyway. So there's algorithms used to estimate gradients, for instance, for problems and so on. This goes in the right direction of meta learning and so on. Where you don't know what your learning rate should be. You don't know, because there are so many hyperparameters. You don't know any of that. And there is also the point of why having one hyperparameter, one learning rate for the entire, for the entire architecture uniformly, right? So
the price to pay comes before you need it in real time.
Yeah, exactly. That's exactly the problem, because then you have to have some meta or some algorithm that estimates all these parameters in between, gradients, etc. And if you can run this in real time, all of it in joint optimization, I doubt it. So that's
Anyway, maybe
I think.
Already use of R
Oh yeah.
Discussions. I think we should have a break anyways.
Yeah.
I would say let's cut it to 15 minutes, and when we come
So.
back, then Simon will start this last lecture, and then we go on to the.
Yeah. So for the online audience, we will have a 15 minutes break now. Thank you. Sorry for the online audience for a couple of minutes delay.
So, welcome to the last presentation of our bootcamp. This is the closing lecture, which then will be going into the hands-on session. So there is an overlap. And I hope we can make it. It's a lot of material, but it's not stuffed with formulas. So before we had the presentation of Marius of the PPO and all its details, which is very technical, and I want to bring it up to a higher level perspective. So it should be conceptual, just a few formulas, but we can discuss every detail. And I will start with some practical questions, which were raised anyways during the last conversations and talks. And I will give some remarks, general remarks on reinforcement learning. I will show you what you can do if you know how the world works as an excursion, which fits very well to some of the talks of today. How to find the basis of the decision, which goes also towards some discussions we had about when is it Markov, when not, what to do if it's not Markov, and so on. I will discuss the basic challenges of reinforcement learning algorithms, which concerns more the algorithmic side, not the problem side. Maybe we have time to discuss some of the philosophical perspectives, and we will have some final remarks, which should then open maybe the discussion also for the hands-on session. All right. So let's start with practical questions. So, most important, don't give up. Try to understand your problem well. So you have to understand what you want to solve. You have to frame it as good as you can before you start doing any attempt to solve it, in my opinion. So it has to define what is the problem, what is the scope of the problem. And then maybe you can phrase it as an MTB, maybe not. Yeah, this is the mathematical framework for all our reinforcement learning agents. We have to define the variables we heard, state, action, reward function. The objective should be clear. This means what is the design of our reward? And only then you start to look for the right tool to solve it, in my opinion. So is reinforcement learning the right tool? This was raised several times already. Should you do reinforcement learning? If yes, yes, sorry. Yes, you should, and you should know which algorithm to use. Okay? If not, what are alternatives? And also, when you design your experiment, how to measure the success or the generalization of our algorithm. Define some metrics. What can you measure in your problem? Is it a convergence rate? Is it a cumulative reward? Try to find benchmarks. And all this somehow is addressed in the tutorial, as we will see. And we will also discuss the problem during this lecture. We solved them in the tutorial. And some or almost all ideas should also be shown to you in the tutorial. Then you can try it hands-on. So, some general remarks on reinforcement learning. What is it today? It has its position in artificial intelligence. Historically, it's from the theoretical side part of AI and machine learning, but it's more a community of researchers who try to apply specific tools. One could say it's data-driven dynamic programming people try to do with reinforcement learning. And you do that when you have little knowledge about the probabilistic mechanics of your data and your rewards and how they change over time. And the idea is to probe the system to find the dynamics and to solve the control problem. And it belongs to the general field of sequential decision making, which was already mentioned by Catherine in the beginning, which is a huge field. And also there you will find attempts to solve these problems. Okay? But it's a really powerful concept. So this is the sentence the students have to learn over one semester here. This is learning how to make good decisions, which has this learning. What is learning? Everybody here should know now what learning is. We learn from experience. We learn from data. We learn how to make good decisions. We set our problem into a context, and then it said something is good and something is bad, and we can have some uncertainty in our problem. But this is a very fundamental question, and maybe it defines intelligence. If you are good in this, you can move smartly in the world, and you have an easy life. So how is it done in reinforcement learning? And this is what I really like about reinforcement learning, is we start with information. This is always how we start to probe our world. We collect some data from observations, and then we start to model. And as soon as we have the model, we have to decide something. We develop models only to make decisions, right? We derive a strategy out of our model in order to do something afterwards. And usually the story ends here. And this is not the case in reinforcement learning, because it might be that the decisions we make, the policy we derive out of our model, invalidate our model itself. So the model itself is not aware of the consequences of its own policy. And this is what reinforcement learning tries to do. It tries to close this loop in getting decisions, getting information, taking a decision, getting new information, how these decisions influence the world, and so on. Okay? So it's an active paradigm versus prediction usually static. So let's compare it quickly to other AI paradigms. Here we have supervised learning, AI planning, unsupervised learning, and reinforcement learning. And all of these 4 disciplines have something to do with optimization. Planning usually assumes a model, so we don't learn the model from experience. We give it the model, and it should plan within the model. Nevertheless, it should be able to generalize, and it can deal with delayed consequences, because you can plan ahead and can see what outcome would be desired if the reward only shows up after some steps, for example. This is not the case in supervised and unsupervised learning. They, of course, learn from data, they optimize, and they should generalize. And then there is this learning from experience and exploration part, which is then somehow in addition in reinforcement learning compared to the others. So it contains a lot of different components. And as we saw today very often, what is the objective? I just repeat it. I think it's good. This I think is one of the formula slides, but you saw it very often today. So we have this interaction loop, and then we can interact for some steps, which is called the horizon. We will see it several times now in the talk. We have a policy here, which can be stochastic, which tells us what the action is if we observe a state, and this generates a trajectory of initial state, initial action, till state action, till the horizon. This is then a trajectory. Here the Markov assumption goes in, which was discussed today. This is the policy. You have an independent product, probabilistically speaking, and this generates a trajectory, and you want to optimize the sum of the cumulative reward over this horizon, over this policy or other trajectories generated by the policy. This is the goal. Okay? It's an optimization problem, and it was in BPO formulated as an optimization problem. All right? So this is the landscape, by far not complete. Just to give you an overview, finally, again, we start here with our Markov decision problem. If we have a finite MDB, we can use tabular methods. And then, if we know everything about this, we can use exact methods. This is called dynamic programming. I will explain this in a second again. We saw it in the initial lecture of Catherine. And if we don't know the transition probabilities, we can use sampling. And then we are in the world of Q-learning or Monte Carlo. This is the first historical branch, you would say. This was 1990 around when this was discovered. But this sets more or less how it works. Yeah, and then if you don't have a finite MDB, you have to play these tricks, as we learned, using function approximation or whatever. And then again, you end up in sampling methods, and you either use policy gradients as the PPO, the proximal policy optimization, or the trust region policy optimization, or you are value-based, like DDBG or DD3. And they are all ectocritic. So this is the modern reinforcement learning world. And then there is something which is a model-based reinforcement learning, which was only mentioned but not described. And I want to discuss this now. So what is if you know how the world works? What if we know the transition probability that being in a state, taking an action, what is the probability ending up in the next state? And also, we know the reward function. So, okay, we said we have this dynamic programming approach where you use the Bellman equation, which is just a backward recursion, because we say if the last step to the if the last step to the goal is the best option, then okay, I can reduce the problem to go here. If this step to here is the best option, I can reduce it to here. So this is the initial idea of dynamic programming. This is the basis of all value-based methods we saw so far. Right? So just to show what the solution of this is. So this is our goal. And as I said, I'm here, I go to here, I'm here, I go to here, I'm here, I go to here. But I solve a policy for all possible states in dynamic programming. And this is a closed loop solution, because if I'm here, I go here, I know what to do here, I know what to do here. So it's really a general solution if you want so. Yeah? This is solved by, in the tabular case, value iteration or policy iteration, which is in Sutton and Pato. But it was also mentioned in the talk of Thomas. We can also use the calculus of variation, so the Bontragen maximum principle, which is only a necessary condition. Dynamic programming gives us a sufficient condition, but the idea is that we are in an initial state and we want to go to a final state, and the calculus of variation, or this maximum principle, tells us what the optimal trajectory to go there is. Okay, So we need an initial state, and we go to a final state in an open loop fashion. This means I plan ahead here. And I can only do this if I have a sufficient model. But the interesting part here is that I can now force the trajectory to fulfill some constraints. This is the huge difference between, if you want to, reinforcement learning and control theory, because I can plan within specific constraints, and I can give guarantees if my model is well suited. Yeah? But the main problem here is that it's open loop. It cannot stabilize the system. So assuming I'm here and I plan ahead, but then there happens a perturbation, I would be far off finally. Okay? So the idea now, and it was mentioned already, of what is called model predictive control is to bring both worlds together. So this belongs to the field of optimal control, where we have these open loop ideas I just discussed with Bontragen's maximum principle, where we have several solution methods, but we concentrate only on the direct solution, which is just more or less an optimization as you know it. It can be a numerical optimization respecting some constraints, and we will see this in the tutorial. The other one would be solving integral equations and with boundary methods. And then we have this closed loop idea, where we have this principle of optimality, and here we concentrate on discrete time dynamic programming. And MPC sits somehow in the middle. So we have this optimization respecting some constraints, but we do it in an open, in a closed loop way. So these are the only formulas which are left. I explain now. This is the objective of reinforcement learning anyways, just rewritten in a different form, but this is just the expected cumulative reward with some noise term here. This is a random variable, and this is the formulation as an optimization problem of the reinforcement learning task, because this is constrained to the dynamics of the world. This tells us that this is subject to, if I'm in a state and I take an action, that I end up in the next state. The policy has to fulfill it, and we have a starting position. And MPC instead not solves the full problem, but splits it up into a specific horizon and the rest. Yeah? We saw this idea several times already. And this is how it works. So it's very intuitive once you understand it. So this is our reference, our goal trajectory. This is where we are. This is the future. This is the past. This is our measured output. This means we want to go from here to here. In this case, these are the past actions, and now we are here and we have to decide what to do. This is the predicted output by the model. This is the prediction horizon, so we think a few steps ahead only, but not till the end, because otherwise we cannot solve the problem. Okay? And then we predict the best, in an optimization way, the best trajectory. And we just implement the first step. And then we do this again and again and again. So you always solve in each step an optimization problem, which is a computational burden, but we have some guarantees in the best case. All right?
Simon, is not the minimize for the MPC? I'm always confused, or is it really?
Yeah. I mix it up. In control theory, you minimize the cost. In reinforcement learning, you maximize the reward. You just switch the sign.
I always do the same. I know why.
Okay. So here I've written reward. So we maximize, but usually you have the cost here, and then you minimize. So here even is written final cost. So this doesn't make sense. But okay. So now comes the point. Where's the link to reinforcement learning? In reinforcement learning, we don't have a model. So we learn the model. We learn the model from data. This is the standard reinforcement learning loop here. And we just collect data on the way. And with this data, we can start to develop a map of the world internally. And the agent can think or hallucinate about the consequences of the actions and has not to learn directly from the system, from the feedback of the system. Of course, the model is always wrong, but it's cheap to plan here. So this makes algorithms extremely sample efficient. And so I want to give you an example, which we then have at the end of the tutorial, which is a data-driven MPC, where we learn the model from the data. And then we start to optimize in this model predictive control way, that we don't roll out the full trajectory, because these lines here indicate that this would be done by the model, but it's wrong. So we just take the first step, and then we are here. We take the first step, and so on, and then we follow more or less a good path. Yeah.
Just a question. When you say that we learn a model, you say we are learning like the environment. So what we...
The dynamics of the model, which is the Markov kernel we learn.
We just have like data about the like observation of the dynamics, and we try to infer a model.
Yes, exactly. And also we have the reward. We can, if we are in the reinforcement learning loop, we don't have an idea about the reward.
Yes.
So we can have an idea, but it is a function of state and action always, the reward. So either we can infer it from the model analytically or in some form, or we have to learn it in addition if we don't have any idea. Okay, but this is learned. State, action, next state. And this is then an inference problem. But I show it now on an example. Okay, we do this optimization in this model. We can use maybe models which are differentiable, which is an advantage. Yeah? We have to take several design decisions into account on what kind of model do we take, what kind of optimization do we take, what are the constraints, the safety constraints. And then we apply only the first action. We collect new data and run this, improve the model and run this optimization again. This is the idea of data-driven MPC. Yeah? And in difference, model-based reinforcement learning, classical model-based reinforcement learning would not run an optimization, but would run the algorithms we learned today about how to optimize, how to find a good policy. This is really a classical numerical optimization. So, okay, and in the end, what we have is a model, and then we always can use it to optimize. Yeah, we have a model of the dynamics finally. So, I introduced something here which is called Gaussian processes. This is shallow learning. This is not deep learning. This is a non-parametric function approximator, which has several advantages over deep neural network and several disadvantages. But one of the major advantages is the following. Here's a sketch. So this is a data-driven approach, and we have two problems in our model. Because if our model is always wrong. A model is always wrong. Yeah? But if it's too wrong, we cannot optimize in a good way. So it would be good if we would have a model which is aware of what it knows and what it doesn't know. Yeah? And this is called the epistemic uncertainty. This is due to the lack of data. So if we would have sufficient data, the model would be perfect. But because we don't have sufficient data, the model is not perfect. But it has, and this is a strength of the GPs, a knowledge where it doesn't have data. And we can take this into account in the planning. Because otherwise we have a model bias, and this thing collapses very quickly. And everybody who does model-based reinforcement learning experiences this at least once, that it just doesn't perform at all. So if the complicated reinforcement learning, but also learning the model, and the combination is very tricky. But we will come to this in a second. So this is the epistemic uncertainty. The model knows, okay, I don't know much here, so we can take this into account. While we have also the aleatoric uncertainty, which is the intrinsic uncertainty of our problem, which can be the measurement uncertainty, for example. which would be here. We have a data point. Okay, the uncertainty here is shaded, is not so large, but still there's an uncertainty. Okay, so we cannot do better, no matter how much data we would get. This is called aleatoric uncertainty. And yeah, this is what a Gaussian process assumes. So it assumes some normal distributed noise around the data. And I don't go into the details. We can discuss this in the hands-on then, how we, what kind of implementation we use there. But if you use radial basis function, which is more or less the starting point in Gaussian processes, you can propagate this uncertainty in an analytic way, which then accelerates the optimization. And what you do is we said, okay, we had this starting point and the end point, and optimization usually, unless you use a sort of robust optimization, can only work on deterministic systems. So what you can do, for example, is you propagate the mean and the covariance matrix, and in such a way you solve a deterministic problem, including the uncertainty. And then you would optimize for the expected reward under this distribution. Okay, this was a short excursus to MPC and model-based reinforcement learning. So let's discuss the basis of the decisions quickly. When we do reinforcement learning, we usually have this problem. At least we assume we have it. We have this happy robot living in a happy MTB, and then we attack it. But this is usually not the case. Usually, we don't have the full information. We just have a partially observable space we live in. And just to give you the definition of a BOM-TB, it's just an extension of the MTB where you have, instead of the state, the direct state observation, you have observations out of an observation space. And then you have a function which tells you what is the probability that a state emits an observation. So this is an additional burden you have when you have BOM-TB. So the world is a BOM-TB world. So we live all in a BOM-TB world. We perform very well, which is exciting. But this is BOM-TB land. So if you go to the literature, it's like, whoa, oh my God. This is a very nice illustration from Koch and Derfer. And yeah, this just should illustrate we know BOM-TB so for a while, and we try to attack it with many, many tools. Yeah. So let's discuss quickly, and it was mentioned several times, what to do in this case. So we have our world state, and the world emits observations. And from these observations, we have to somehow derive features. Yeah? So we have this internal representation of our agent, from where on we base our decisions. This is what the basis of our decisions is. This is why this is so important, because if we don't do it right, we cannot decide well. If you don't know where we are, we don't know if we should go in a dark room, go forward or backward if there is an obstacle, right? So, and then we expect to build an MTB out of this internal representation, which can be a history of observations and actions and rewards and what you want, but it should be sufficient statistics. Right, so how bad is this story? In a linear case, and this was introduced by you, Thomas, you had a feedback controller. You introduced a static feedback controller with this K-matrix, right? This is the easiest problem if you have a model. But if you don't observe the state directly, but you have to infer the state, the problem is NB hard, even in this very simple case. And generally, it's very hard to find good solutions. In practice, we heard from Catherine, it rarely is impossible if you do it right, but I just want you to know that this is a really stupid thing if you make a mistake here. And in control theory, there's something called the Kalman filtering, which can be shown that, or let's begin before. So what we can do is we separate the problem into a filtering problem that we find a good feature and a control problem. The filtering problem is a prediction problem, and then we say, okay, we are really certain about this feature we found there, and then we solve our control problem. This is called certainty equivalence. And one can show in some cases that this is really the optimal thing you can do. Okay? This is done in robotics and everywhere if you can do it. Just to have this said. But as we learned today, so we now try to frame our problem a bit better. That's not all, because there is this tricky outer loop which says how to deal with the algorithms. Once, let's assume I solved this, now I'm ready to go, and now we discuss challenges of our algorithm on top of this. This is the challenges with the basic algorithms. And I have to emphasize here that most of the ideas are from Sergey Levine's lecture, so I don't take any credits for this. I used many of these ideas because he gives such a good lecture that, I just want to share it here. And I just apply it to another problem than he does. But, okay, this first slide is even from David Silver, which is much earlier, which shows you the world of the different reinforcement learning strategies. So we heard that there is this model-free world, where we assume to know nothing, we just probe the system, and we have these value-based approaches. We have the policy-based approaches. Value-based means that I concentrate on the Q functions and the value functions, and from there on I derive a policy. Or I directly concentrate on the policy, like in PPO, then it's policy-based, or I'm somewhere in the middle, or I develop on top, as we saw, a model, and then we can play this together with the model, and then we are in the model-based world of reinforcement learning. So what about the stability with all these approaches and the hyperparameter tuning? I hope this is readable. I try to take these colors here that you know where we are. But designing reinforcement learning, designing stable reinforcement learning algorithms is not easy. It's a very difficult thing. And we saw PPO, it fills a lecture, and you don't get everything there, and you don't cover every aspect, right? So this is a huge monster already. Here, what we see is what we had yesterday in the tutorial with the hyperparameters of Q-learning or value-based approaches. We had this deadly triad I mentioned, where we know that the Bellman operator in combination with function approximation is not a contraction operator necessarily anymore. And it might fail, and we don't know in advance. So DQN might works really fast, or might fail really fast. And we cannot say. It really depends on so many components. Yeah. So we don't have any guarantees here. Yeah. So we have many sources for problems, many hyperparameters, like how to design, how to update the target network, what is a good buffer size for the Ripley buffer, what learning rate should I choose, and so on. But we cannot get rid of this easily. Also, we saw in a keynote from Razvan that what can we transfer, what we learned from supervised learning, from deep learning to reinforcement learning, given this deadly triad. These are gradient-based methods now. We are here. So we saw that they have a very high variance. They need a lot of samples, as we will see, but they're a bit more stable. And here we would have parameters like batch size. The design of the baseline was a big subject. And then model-based is even more complicated. You have to decide what kind of model you use, and then on top of this you have all these hyperparameters. It can be highly non-trivial. Here is something which is mentioned as Steiner style, which is the most intuitive approach you would take. What you do there is you have your MTB, you probe the MTB, you develop a model, and then you just take a model-free algorithm and run it on the model and hope that it does something. And this is done in a loop. This is called Steiner style, just that you know. Yeah. Okay, and then you can run into the trap that the model is exploited, which happens really fastly, and then you don't get any good data anymore afterwards. So this is a real-world application here. So what you would do is you run your hyperparameter scan, but you cannot do this in real-world problems. Yeah? Usually, a simulator is not very representative. If you want, for example, to control such a machine, which I did years ago, and what we did here, which is maybe a good idea, but it worked in this case, we had an idea on how it roughly works. We used this rough idea to find the right hyperparameters for our reinforcement learning agent in order then to go there and train it on the real machine. So this was simulation-based hyperparameter search, if you want so. But the simulation was really bad. Nevertheless, we were able to do it. Okay, what can research do here and tries to do? We saw the DRBO today already. We can also, there are many attempts to stabilize algorithms where you try to get the best of the value-based and the model-based, the policy-based world, like here where you give guarantees at least on the batches, for example, in this safe RL and high confidence policy improvement. Or you have algorithms which adjust their parameters according to the problem. These are also attempts. Yes, sorry.
Just a short question on the previous slide. So sample complexity.
Yeah.
Is this a definition that is also that literature sticks to? So it's like ball clock time times the number of steps, or so.
Well, I'm not quite sure if this definition here, if this is very common. You see several things actually, but let's have it as it is here, I would say, for the moment. Yeah, there's something which is called sample efficiency, which tells you how many samples you need without taking the computation into account, and so on. Okay, more research is needed here, of course. So this is now the problem we will discuss in our tutorial then. So I introduce it here, and I also take this as the basis of the discussions concerning the sample efficiency now. This is the CERN Advanced Wake Field Experiment, short AWAKE. This sits here. This is the CERN accelerator complex with all the experiments and accelerators. And usually a particle starts here with a LINAC and then goes into a circular accelerator, is accelerated to some energy, and then to the next one, accelerated to higher energy, and so on. And here in this case, we use protons from the SPS and send it here to this AWAKE experiment. And then they are entering a plasma chamber where they produce wake fields. And these wake fields then, they have really such a gradient, and then they push electrons to very high energies in a very short distance. This is not the problem we solve, but I just want to show you. And these electrons are generated here with a source and then an RF gun, and then they have to go through this beam pipe here till the plasma. It's not shown here. And here the interaction with the protons would happen. And what you can do there is in 10 meters you can accelerate electrons to energies where you would need kilometers of acceleration in a linear accelerator. It's a proof of principle experiment. And this is how it looks like, a lot of cables. And we concentrate on this part in our tutorial. So what we want to solve is we want here an electron goes through this cascade of elements, and we want to force it on a specific target trajectory. So we measure the distance to our target, and we want in one step or several steps to correct it. So, but this is one step. The full sequence here is one step. Okay, just that you know. And we have here measurements along the line, which are the positions, and we have full state observation. And we have magnets to control the trajectory, to kick it into a specific direction. So here this element can kick the beam up or down. Then we measure where we are. We can go to the next, can kick it up and down, and so on. Okay? So I don't have to explain it twice. But I think, because this is a bit tricky, that this is a trajectory, and in reinforcement learning we have a trajectory. But this is one trajectory here is one state in reinforcement learning then. Okay? So let's have a look. This was one of the first experiments I did at CERN. What is the sample complexity of this? Here we have a good simulation, to be honest. And I tried it on the simulation. So this is the starting point. This is going down or going up in sample efficiency, going down in samples needed from gradient-free methods. We didn't discuss this today because we entered gradient-based search already. But you can just throw this optimization problem of reinforcement learning in a huge optimizer, and only in specific cases, if it's small enough, you can solve it. But you can do this, and there are several methods to do so. But they are extremely inefficient, so you cannot even run this on a real system ever. If you go down and use gradient information, but not in a batch way, but just simple gradient steps, then you are in these actor-critic methods like this A3C. They have the advantage that they are highly parallelizable and very fast in computation. So this is sometimes the way to go. And then we come to trust region policy optimization and proximal policy optimization. And here for our problem, for several dynamics, I don't discuss this, but these are just variations of the problem, we need around 50,000 samples. And if one iteration takes, I don't know, 1 second or 3 seconds, then you can imagine that you wait a long time here, maybe a month. Then you can go down. This is, by the way, a Bayesian approach, because this was a question yesterday from the audience. This is the maximum a posterior policy optimization here. This was used in the Tokamak paper of DeepMind. It's a very nice offline policy optimization algorithm, the only one I know actually. Yeah, we go down a factor already by 10. The next one are the value-based, and now you see why this is a good thing always, although we have stability problems. We are down at 500 iterations here, which then is a question of hours. Then we go to model-based. This is a model-based policy optimization, an interesting algorithm where you use a dyna style. As I said, we just apply model-free onto a learned model, in this case an ensemble of neural networks to capture the uncertainty somehow, with some guarantees, they claim. But at least you see we are now at 100 iterations. Then what we see in the tutorial is the GP-MPC, which goes down even further. This is how in a logarithmic scale goes down here. Okay, this is the sample efficiency, but this is not a full story. Okay, why is this important? Maybe algorithms take a very long time to solve a problem. real application is impossible if you choose the wrong algorithm. Even if you have accurate simulations, they might be very slow, like finite element analysis and all this stuff. So you would also go for a more sample efficient algorithm, although you would train not on reality. And especially when we come to the variation, which happens in reality, it's a really hard limitation. But this is not the full thing, as I said. So this is a graphic which shows you more or less how handy an algorithm is versus how many samples it needs. And this is why usually the common choice, and also why BPO is so popular, that you go for an algorithm which is not so sample efficient, but you don't have to tune that many things. Yeah, this is the policy optimization algorithms. Okay, so we see here samples grow, stability grows, samples go down, hyperparameter tuning grows, computation time grows, and also the model bias plays a role. And from here on, you would say we can start real-world applications somewhere in this between on-policy, off-policy, actor-critic. Yeah, so this was mentioned. I just quickly show it again. Here, the advantages and disadvantages of value-based versus model-based, and we are somewhere in the middle. But value-based is fast but biased and can be offline. We don't have any guarantees. Usually it's only deterministic, but the software critic does not as standard Q-learning, so it allows for stochastic policies. Here are some examples. Deterministic, deep deterministic policy gradient, then twin delayed policy gradient, and then the DQN algorithm we saw in the first tutorial. And here on this side, we have the policy-based, which suffer from high variance. They are on policy, but they are very stable. And they only give you local guarantees. But they give you guarantees, at least. But it's a gradient-based method, so they run to the local optimum, usually, of course. And they are usually very fast to be computed. OK. Of course, what can research do? Better model-based algorithms, faster algorithms, soft actor critic I just mentioned, DD3, these are value-based algorithms which only go for stability, to improve the stability, that they are not so sensitive. Or you can use prior knowledge, maybe. And I show you an example here. Meta-learning was mentioned. Meta-reinforcement learning is an example I want to show you now quickly as a short excursion. So just quickly, what is meta-reinforcement learning? Meta-learning is learn to learn. Meta-reinforcement learning is learn to learn reinforcement learning. But I explain this here. So let's say we want to learn to hike very quickly. We learn to ski very quickly. We learn to ride a horse very quickly, to stand very quickly, ride a bicycle, and so on. And then we hope that from this learning, we learn how to learn fast on a totally new task. This is meta-reinforcement learning. Yeah? So you have a distribution of MTBs, of tasks. You train on this. You try to find a good spot in the parameter space there, and then you can quickly adapt to any new task. So there's a fine-tuning step afterwards. This might really solve your problem. And just to show you, this was 2 weeks ago presented here at the conference, an experiment I run. This is not a TRPO, not a PPO, but something like this, like a policy gradient method on the awake problem over specific test tasks. And we see if I just randomly initialize my networks, this is called model agnostic meta-learning. We don't have time to go into the detail, but we try to bring the network to the best position to learn as fast as possible all realizations within our distribution. And this is the standard way to do reinforcement learning. You just don't know anything, so you randomly initialize. then you could say, okay, I know more or less the uncertainty of the outcomes, so I just put it into the center. I train on the center task, which helps you then somehow. And if you run a really meta-reinforcement learning, you're up here. So it's very fast and very stable. And I just show you this because this brings an on-policy gradient down to the sample efficiency of maybe a model-based approach with the stability guarantees. So you really put it there and it goes just up in a few steps. This is really cool. Yeah? So this mitigates maybe some problems. It's just a suggestion. And this was demonstrated on a machine. Okay, let's compare reinforcement learning a bit to other approaches, to supervised learning. So reinforcement learning has a problem, a huge problem. What we generally do, like here, what made deep learning so great is that we have a lot of data, large-scale data. We have a lot of diversity, and we can really train our algorithms to generalize well. We have test problems, and they never saw, and they just perform well on this, which is not the case in reinforcement learning if you are fair, because you run a training on an MTB, and you evaluate on the same problem in principle, right? So this is usually small scale. You try to optimize the optimization, so you want to optimize as good as possible. But the question is, where is the generalization here? So as I said, there's a huge problem. This is supervised learning. This is from Sergey Levine. So once we collect data from the real world, then we go to our office, and then we run our supervised learning in the office with this data. And then you can really tune the thing easily. Whereas in reinforcement learning, you would have this interaction over many iterations with the real world. So this is a tricky problem. And on top of this, you would have this outer loop I mentioned before. We all experienced yesterday maybe when it comes to the hyperparameter, or you change a tiny thing in your problem and you can run the training again. Then you change a tiny thing in your problem and you can run this training again, and it looks totally different. So this is really challenging. And let's say this is a result of the DRBO who learns to run and gives very good results. Nowadays, it's around 6 hours of training or something on this simulation. And then finally, you get a robot or this humanoid which runs somehow in a meaningful way, but only on an infinitely extended plane. This has nothing to do with the reality, right? The reality looks like this. So what to do? Maybe offline policy or offline reinforcement learning, which has to be off policy, is the solution. That we develop better off-policy algorithms, that we just collect the data once, and then we just train on this data as we would do it in a supervised fashion. Or we use multitask learning, which is somehow related to the meta-reinforcement learning. The only difference maybe is that you, in the beginning, so what the agent should learn to solve different tasks, like to run on this plane, to run on these hills, to run on water you cannot run, or in the water if it's not too deep, you can. Yeah. So in the beginning, you sample one of these tasks, and then you train. So the agent samples one of these tasks and then is trained on this specific task, and then in the end, it should quickly realize where it is, and then it can do the problem. So, okay. Here are some ideas in papers, what you can do. Again, meta-learning is mentioned here, but also unsupervised or weakly supervised learning would be an option. In unsupervised learning, you train the agent, or the agent has some goals which don't correspond to a specific goal we define, but it learns to for example, minimize some theoretic information theoretic goals, and then it learns to do some meaningless skills like grabbing an object and dropping it, but it knows then afterwards how to do this act, and then you use this later on when you want to solve a specific task.
The sampling of the tasks is IID, or there's some kind
Random, yes. Well, but the rest is not IID here in this case. This is just, sorry. This is just one idea. But here you sample randomly and then you stay within this MDB.
How is it related to, because I'm a little bit confused. Yesterday, Razvan said that if you teach a robot to hold the ball, and then you ask it to open the drawer and put the ball in the drawer, it doesn't help. Because he said, I remember, if I remember correctly, he said you unlearn some of the things that you learned before.
But this has to do with the function approximator itself, not with the reinforcement learning. But this is true. Yeah, you wash out the information, and then it doesn't know what to do. So you have to set this up carefully.
And
maybe there's.
And it's about also how you learn it. Because you talked about continual learning, where you
Yeah.
learn the task in a sequential manner. So you learn first to do the task of grabbing the ball or opening the drawer, then
Exactly.
the ball and so on. But if you integrate the information, learn that, then you
Here you would go for it to learn it simultaneously, that you don't forget it. Yeah, this is a good point.
if one task is particularly more difficult than the others, and it needs more meta training to get there.
Yeah.
Or should the tasks be more or less the same?
Yeah, there are some restrictions on how you can sample out of this MDB. They should have the same state space, the same action space in the common approach. Also here, of course. Otherwise, you have play tricks, and it gets tricky. And also, if a specific task is harder than others, maybe you can emphasize on this task a bit more. But you need more training to somehow solve the task then. These are all consequent problems then afterwards. Okay, I'm not sure how long I spoke already, so. Well, it's an hour already. Okay, all right. Well, then we go quickly through some philosophical perspectives. So you can use reinforcement learning as an engineering tool. Reinforcement learning might be the only tool which brings AI to reality, and maybe it's a way to do universal learning. I'm actually more busy with the first paradigm, but the third is why I'm doing reinforcement learning. The first is reinforcement learning as an engineering tool means that we try to invert the physics. So this is how we landed on the moon, and we saw this also in the talk today. We have some idea of the equations of motion, and then we design a controller. And this then helps us to reach our target. And this is meant by inverting. So we know what to do in order to achieve something. We know where the equations lead to, but we don't know exactly when we want to achieve something, how to do it. And so we invert it, we find the right actions. And the same thing, here this is control theoretical, because we have the model, we just do the mathematics, and then it's done in a feedback way, but nevertheless, the controller itself doesn't adapt to the problem anymore. We can also do this with reinforcement learning. If you think about complicated simulations, you can use reinforcement learning as an inverting tool to solve your problems. Yeah, it's a very powerful engine to do that. Nevertheless, we need the simulations to use it. We need, like in control theory, a model. And then we can calculate the model, but nevertheless, it might give us good ideas. And this is what most of us do, I think, here in the room. Then there's something else, which is a reinforcement learning and the real world, or in this case, AI and the real world. We have here Moravec's paradox, which says that what seems for us complicated is done by the computer easily, and what seems for us easy, the computer is not able to do. So this has to do with the evolution. We had first learned to walk, and then at one point we started to play chess. And so we think now chess is complicated, but learning to walk is complicated. We live in a very complicated universe, but we are not aware how well we are optimized on surviving in the world already. And this leads to the paradox that abstract thinking is for us complicated, and the computer went the exact opposite direction. We started to solve chess, but we cannot design a robot who can do the laundry for us at the moment. This is, by the way, also why you see this. This is Garry Kasparov, 1969, was defeated by Deep Blue, by IBM. And he doesn't play against a robot, he plays against a human who reads from the screen what to do next. Also here, Lee Sedol, in the AlphaGo match, there was also a guy moving the stones for the computer. So the game for us is complicated, but the movement is easy. But the movement is really hard for a robot or for AI to be done. So maybe reinforcement learning is the only way to overcome these limitations. This is what I wanted to say here. Okay, and also real-world training is full of problems. Just a really nice idea can be, for example, here, if you want to learn a robot to make coffee for you, it will drop the cup very often. So what you can do then is to make this a closed loop. You have another robot who learns to pick up cups and put it again to the first robot. So you could try to learn a closed loop in such a way, right? Yeah. This is interesting, as I said, because it might be the only way to overcome especially unexpected situations in reality. Because we are good, if something unexpected happens, we adapt quickly. But AI systems are very bad at this. So Sergey Levine gives the example, we can program an oil tanker to go to another continent easily. The navigation problem is easy. But if the engine breaks, you have to have a person on this ship that it repairs the engine. Otherwise, this is the end of the story. Okay? And reality has, or the problem you would tackle in this case has to be interesting enough that it shows new behavior. The last idea is reinforcement learning as a universal learning approach. Here we have the success of deep learning. We have a lot of data, we have huge models. All this data has to be labeled. This was a problem at one point, or is a problem since ever. So then we saw the rise of these LLMs, where they learned not to label, or they could learn without having labels for everything, but having labels for just a few tasks. And we had the semi-supervised learning, where you could use the internet to somehow train a parametric model which somehow learns this distribution of the human knowledge or the human language. And reinforcement learning might be a way, because this has severe limitations. You know, it's really hard to find the right prompt, for example. It can, you know exactly what to do, but the LLM doesn't do what you want it to do, because this might be a really weird distribution. We are not fully aware of this, because there's a lot of unsupervised stuff in there. So reinforcement learning might be a way to really come back to the problem where I started with the first or the third slide, that we try to find decisions. So we might use reinforcement learning here in this context to use this large amount of data to get an idea of what is possible in the world. And then we can use this data to train our agent on these problems to fulfill some tasks. And I want to close here this part and just want to show you some things which are going on in Salzburg. This is Juan, who does this. Whoa, there's even music. Sorry for that. But enjoy the show. This is what Juan does. He tries to make these nautic robots autonomous using reinforcement learning. Then Sabrina, who should be here, is sick. He does a multi-agent reinforcement learning for device-to-device communication. Reo did a PhD on optimizing assembly lines using reinforcement learning. Then Sarah does energy consumption minimization of big plants and companies. We had some presentation on this. Then we have here Sasha, who did interpretable reinforcement learning, which could be applied in medicine, for example. He tried to treat or sepsis, I think. What is the best sequence of actions if a person has sepsis, if you have some information. Gesine is not here in Salzburg, but she tries to use reinforcement learning to automatize microscope. Then Leander is here, who is working to use reinforcement learning in quantum computation, but not in a quantum mechanic way or in a quantum computational way, but to optimize the optimizers for quantum computing. Is this correct? I'm confusing, sorry. But ask him for the details, but there are applications. And also, Georg is here, who has his little robot and does his PhD on cyber physical systems. Yeah, and also we do a lot of accelerator physics control problems. Just some final remarks. I'm quite over time, sorry for that. But I think this is an important slide again, and then we do a short break. So when you do reinforcement learning, think about your problem really carefully. Always in life, think about your problems carefully, maybe. Yeah? And then decide how to formulate and solve them. Choose the right algorithms. We heard this. There is no one-fitted-all solution in machine learning in general, in reinforcement learning in a special. Think how to evaluate your progress, how to design your experiment that you're really aware of, is there an improvement or not? Should I give up or not? Right? Never give up. Was this a paper? I think. Be brave, maybe. Try something new, completely new from time to time. Don't stick too much on what is out there if it doesn't work. Maybe something new is needed. Think outside the box, like the second robot who picks up the cup. And most importantly, you're not alone, especially when people start with reinforcement learning in their master or PhD thesis. This is a really hard part of their life. Yes, Hannes says yes. So you're not alone. We are here, we are a community. So search for help, discuss with people, because it's a lot of experience you need if you want to do reinforcement learning, in my impression. Yeah, thanks. That's it with the closing lecture. We have this time to discuss right now. Let's say we stop. Here are just some references. And I want to say these slides are available online then in the same kit as the tutorial, because this was a question I got very often. And it's on YouTube, the videos you can rewatch. This is what you mean?
Yes, there's also, but also ended for the online session.
I will do now. Yeah, okay. Goodbye, online people. Thanks for being here.
And tomorrow we're not recording.
Exactly. Tomorrow there's no recording. We just have direct discussions, which is a bit hard. to do in this way. And you show me how to stop the recording. I stopped the voice now. So I should say goodbye like this.
Thanks everyone online.
Yeah,
Bye.
thanks everyone.